everybody. Hello. Am I visible and audible? Yes, guys. Am I audible and visible? Quickly go ahead and let me know, everyone. Are you all able to see me and hear me? No? Yes? All right. Namaskara everybody, a very warm vanakkam to Vedantu JEE English channel. Yes, as I always say, Andariki Namaskaram, Ellargu Swagatam. This is me, your master teacher, Nabamita Bhattacharya, and today we are here to study this chapter called as Thermodynamics, everybody. So what's up and how is the Josh, everybody? Quickly go ahead and let me know. Everyone. Are you all able to see me and hear me? And let us start with the session. What do you all say? Let us start with the session, everybody. Are you all able to see me and hear me? Yes, and I hope that you all are sitting with a pen and paper, because in today's session, we are going to complete the full chapter thermodynamics. So there is a possibility that I might skip out a little bit on the problems, because problems we can anyway, sit and do it all together, isn't it? We can do the problems later on, isn't it? Can I watch this for neat? Yes, absolutely, you can. However, my session is going to be a little bit more inclined towards the JEE. I hope you don't mind, but yes, I will be covering the complete NCERT. So sit back, relax, watch it with a popcorn, and do not forget to write down whatever I tell you. Yes, everybody, yes. JEE Menti, we will do this week once both Pratik sir, me, and if possible even Puneet sir, but I don't know, Puneet sir is probably hospitalized, he's not well. So if we all are there, then together we will do it, and if not, Pratik sir and I will do it. Okay, all right, so shall we begin, guys? Are you all with me? Shall we begin? I'm good, cute Bandar. How are you? At a long time, cute Bandar. Where were you all these days? Chocolate boy is there, jawbreaker is there, Janvi is there. When will you do equilibrium? But I'll do, yeah. Chill. I promise. See, mark some, your whole syllabus will be completed. Don't worry about that. But I will keep doing, yeah. I can't promise, because I promise, once I promise, no, I can't follow it. I told you, right? I have a problem with following rules. I can't follow rules. And I can't keep promises. So I'll do it. One thing is sure, that your syllabus will get completed. That is for sure. But apart from that, I don't want to promise anything. So, let's start. What do you all say? Let's start. Hi, Abhinaya. Hello, Peddi Anjali. Hi, Jishan. Hi, everybody. Hi, Amar. Hello. Very good evening. A lot of students are here. That I can see today. This is your first class. This is the first class of thermodynamics, bro. Thermodynamics, first class. And we will complete it. Okay, in one session we will complete it. So there is a possibility that this session will last for at least 3 to 4 hours. We're starting it at 7 o'clock. So 7, it can last till 10:30 or 11. Okay, let's see. So chalo. Now the first question that comes in our mind is, ma'am, why are we studying this chapter? What is the use of studying this chapter? Ma'am, do you really think that we are going to use it when we are a software developer? Maybe no. If you are a software developer, maybe not. But right now your focus is JEE or NEET. NEET, isn't it? Yes. And in that case, you have to study thermodynamics. Now this right here, this whole word that you see, right? Yes. The word that you see, thermodynamics. What is thermo? Thermo means definitely heat, isn't it? Yes. Thermo means heat. Am I right, everybody? Yes. And what is dynamics, bachos? Dynamic means dynamics, kinetics, something that changes, something that keeps changing, isn't it? Yes. That's called as dynamics. So changes, right? Changes. Heat and changes, that is something that we are going to focus in this chapter, right? Now you're going to tell me that, ma'am, heat chapter though in our junior grades we studied, but this chapter was related to physics. Yeah, true. This chapter was related to physics, no doubt about it. But tell me something, when there is a chemical reaction, haven't you heard about something called as exothermic reaction or endothermic reaction? You know, sometimes you have to provide heat for the reaction to happen, or sometimes sometimes when the reaction happens, it releases heat, right? These kind of things always happens, isn't it? Yes. And apart from that, we also know that when you want to break a bond, you have to give some energy, isn't it? And when the bonds are formed, energy is released, isn't it? So basically, there is energy, and there is something that is related to bond and energy. So that means that even in chemistry, we have to study about thermodynamics. Right, everybody? Yes. isn't it? Right? Now, in this chapter, we will be answering certain things about, is a reaction feasible? When do we say that yeah, this reaction is going to happen, right? A lot of times, like for example, we know that disintegration of water happens, electrolysis of water happens, right? Or combination of sodium and Cl ions, it happens, and then they form sodium chloride, right? How did we realize that this reaction can happen? Or I mean, how much of sodium chloride is going to form? How much of sodium and how much of chlorine atoms are going to combine, and how much of sodium chloride is going to form? So basically, to what extent is the chemical reaction going to happen, or to what extent will the chemical reaction proceed? Yes, all of these are, all of these questions are probably what we are going to answer in this session, right? All right. Apart from that, there is also one more thing that you have to understand about thermodynamics, and that is that the laws of thermodynamics, overall, there are 3 laws of thermodynamics. How many laws of thermodynamics that we're going to read about? There are going to be basically 3 laws of thermodynamics that we are going to study about, okay? 3 laws of thermodynamics. And you know what they deal with? These 3 laws of thermodynamics, you know what they deal with? They deal with, bachos, they deal with macroscopic system. Yes, they deal with macroscopic system. All right, what do they deal with? They deal with macroscopic systems. Am I clear, everybody? Now you're going to ask me, ma'am, what is this macroscopic system, ma'am? Papa, ma'am, why do you make it so hard? Somebody has already said, Sabarmati, ma'am, is it hard? If you haven't studied, yes, it is. But I'm going to make it easy for you. Don't worry about it, yeah? I'm going to try and make it absolutely easy for you. All right. So, when we're talking about macroscopy, Asha, how many of you like photography? Do you like photography? Do you like photography? Is there anybody who likes photography? And have you noticed that people who really go close to an insect and then they take a photography, right? Especially in National Geography, you must have seen, right? They take pictures of, like, they zoom into it, and then they call it macro. Call it macro. Why? Because you are basically, what you're doing is you are taking a small insect and you're making it big. Yeah. 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 Why organic chemistry streamed video? It is. It is. See, if I just go here, then if I come down here, let's go to Vedantu Enlight. Let's go to the live session. And then here it is, OG inorganic. See? OG inorganic. See, it's there. What are you saying? It is there. It is there. I can see it. Why can't you see it? Yeah, macro means big size. Very good. Exactly. Yes, you all are right. Okay. Okay, guys, don't disturb right now. Let's finish this chapter. Okay. Do not disturb right now. Let's finish this chapter. And microscope, to everybody knows what. You are all science students. Don't tell me that, ma'am, we do not know what is microscopic. Microscopic, you know, right? You have to use a microscope and then watch them, because microscopic world is so small that you need a microscope to have a look at them. But macroscopic is the world that is around you, the world that you can see, the world that you can see, isn't it? So that is your macroscopic system. So in this particular chapter, thermodynamics, okay, this particular chapter, what we read about is the macroscopic system, basically a large number of molecules. We don't talk about, like, we don't talk about like very small amount of systems and all of these, okay? All right. And also one more thing that you have to keep in mind is, that the laws of thermodynamics, they deal with energy changes of macroscopic systems, not microscopic system. Is this clear, everybody? Is this clear? Right? Now, obviously, in the whole scientific world, or even in our world, right, there is nothing that does not come with disadvantages. Right? There is nothing that does not come with disadvantages. Everything, every law that you study about, most of the laws, there are disadvantages. There are laws that do not hold good for everything, isn't it? And very similarly, even here, even this chapter, it has certain disadvantages. So, let's study about the disadvantages also. Now that I've told you why you should study this chapter, I should also tell you that what are the disadvantages of this chapter, isn't it? So first of all, it can predict the feasibility of the chemical reaction. It can predict the extent to which a chemical reaction can occur. And what did I say? That it can explain the properties. It can explain the properties of matter. But do you know what it fails to tell is, right? It can tell you the extent, but it cannot tell you the path of the reaction. It fails to tell you, okay, fails to tell you the path of reaction, okay, fails to tell you the path of reaction. Clear? All right. Apart from that, what other thing does it fail? It fails to tell you the speed of reaction, okay, fails to tell you the speed of reaction, which is why we have another chapter called as chemical kinetics, isn't it? And it is not available, or it is not applicable for the microscopic environment, okay? Not applicable for microscopic environment or environment. Am I clear with this? Okay. All right. Yes, everybody. Okay. Now we have to understand some chotu basic definitions. Sabarmati, shh, study. You don't know the basic, you will not be able to answer any JEE or NEET question. Understand the basic, only then you will be able to solve the JEE related questions. I'll tell you. Wait, no. Please be here. Okay. Yes. Please be here. Chill. So first of all, what we study here is, the first thing that we have to study here, the first definition is system. How many of you watch Big Boss? How many of you watch Big Boss, guys? In Big Boss, there was this guy, right? He kept saying system. Yeah, that system only we have to say. That system only we have to study, okay? So what is system? A system in thermodynamics, it refers to the part of universe. What is it? Part of universe which is under observation, all right? Part of universe under observation. Yes. All right. Cool. Okay. Yes. Observations are made, and the remaining universe constitutes the surrounding. Okay. So now let's understand what is surrounding. Then we come to something called as surrounding. What is this surrounding? But choose. What is this surrounding, everybody? Yes. Surrounding is basically the rest of the part of the universe, okay, or basically the remaining universe in which the system is not there, okay, all right, the remaining universe or the rest of the universe, is called as surrounding, all right. So now you're going to ask me, so ma'am, then what is universe? Universe is, but choose, the universe is equal to surrounding plus system. Understood this much? Surrounding plus system is your universe. All right, everybody. Is this clear, guys? Is this much clear? Yes, this much is clear. Very good. All right. Now, you know what happens. Obviously, this is not where we stop. We are mostly going to talk about system, right? So, we also have to understand the different types of system, okay? How many different types of system are there, bachus? There are 3 different types of system, and the first one is open system, okay? The first one is, everybody, open system, okay? So what is this open system, everyone? Yes, what is this open system? The open system is basically this. This is an open system where you probably have kept something here, you probably have kept something there, and you know the energy and the matter both are getting exchanged, right? Let's just say that how about if I keep some hot water in this, okay? If I keep some hot water in this glass, you know what will happen? The moment I touch the glass, I will feel that the glass is hot, right? Yes, the glass is hot. And also I will see that after some time, some of the water would have evaporated. So what is happening? Matter is getting exchanged. Yes, the water is getting converted to water vapor, and also when I touch it, I see that it is hot. So what is happening in an open system? In an open system, we get to see that there is exchange of energy as well as matter between system and surroundings. Am I clear with this? Yes, what is it? Exchange of matter as well as as well as energy, as well as energy between system and surroundings. Okay, between system and surrounding. Am I clear? Yes. So possibilities are that let's just say that I make a diagram here. Okay, let's just say that I have a container here. I have a container here, and in this container, if I keep some water, so what is happening here is there is matter that is getting exchanged, the matter that is getting exchanged, as well as energy is also getting exchanged. Okay, all right. Now, as we move ahead, we will also read about there are different types of walls. What will we read about? We will read about different types of walls, and we will read about adiabatic wall, right? So what is this adiabatic wall? When I tell you, then you will understand that, oh ho ho. But right now, do you know what this wall is called as? This wall is called as dithermal wall, because this wall allows the what? This wall allows the exchange of matter and energy. It is called as a dithermal wall. What is it called as? Dithermal wall. Clear? Crystal clear, everybody? Is this clear? Great. Okay. Moving on to next one is closed system. Next one is closed system. So what is this closed system, everybody? The closed system obviously means that basically what if I just keep a lid here? What if I just put a lid on this? If I put a lid on this, okay? If I put a lid on this, then what is happening is I'm saying, obviously, I mean, this is nothing. This is just a coaster. So obviously there will be something. But I will still see that if I keep some hot water here, this glass will definitely be hot. But as soon as I remove the coaster, don't you think that I will see some water droplets? So there is a possible chance, there is just slight bit of chance when I can say that the matter, there is no exchange of matter, but there is exchange of an energy between system and surroundings. Can I say that? Can I say that? Because I will be able to see some droplets of water, isn't it? So yeah, so that is my closed system. So what is happening? What do I say? I say that no exchange of, okay, no exchange of matter, but exchange of energy takes place. But exchange of energy takes place. All right. Yes. So in this case, if I have to make a diagram, I will simply make it like this here, like this, and I will probably keep a lid here. Okay. Let's say that I have kept a lid here. I have kept a lid here. Okay. I have kept a lid here. So what is happening here is matter, and let's write here energy, right? Matter and energy, isn't it? So matter, exchange of matter does not take place, but energy does take place. Clear? All right. And once again, this is also a dithermal wall. What is this? This is also a dithermal wall. Clear, guys? This is also a dithermal wall. All right, everybody? Yes. Now, if I had those thermos flasks, those thermos flasks where you can keep some hot water or cold water and it remains as it is for some time. Obviously, it does not remain as it is for what? For ages and ages, right? You don't get hot water for one whole year if you keep it in thermos flask, right? But it does stay warm for at least a day or maybe for at least 1 or 2 days, right? It does stay like this, isn't it? So for that matter, we can talk about something called as isolated system. What can we call it? We can call it as isolated system, bachos. Okay. What is this isolated system? In an isolated system, there is no exchange of energy or matter between the system and surroundings. Okay. What did I say? No exchange of energy and matter between the system and surrounding. All right. And in this case, bachos, what will happen is you will have an adiabatic wall, because in an adiabatic wall, this matter and energy exchange is not allowed. Okay. This matter and energy exchange is not allowed. So here what happens is I will possibly have a lid here, and I will see that matter or energy matter or energy, both of them, the exchange of both of this is not allowed. And right here, what will I have? I will have an adiabatic wall. Okay, I will have an adiabatic wall. Am I clear? Is this clear, everybody? Okay, is this clear? Cool. All right. Okay. Now let's learn a little bit about how many different types of thermodynamic processes are there. Okay, how many different types of thermodynamic processes are there? Shall we? Okay, let's take a look at thermodynamic processes. Thermodynamic processes. How many different thermodynamic processes are there? Let's take a look at it. Okay, so but before that, what actually is a thermodynamic process? If somebody asks you that what is a thermodynamic process, then what will you say? A thermodynamic process is basically, what happens is operation that brings a change in the state of the system. It is an operation that brings a change in state of system. Okay, all right. What did I say? Operation that brings a change in the, are you guys writing it also with me? Please do write it down so that you have the running notes as well. Okay, brings a change in state of system. All right, this is your thermodynamic process. Now there are 4 different types of thermodynamic process. And what are those 4 different types of thermodynamic process? First of all, we have something called as isothermal process. What do we have? We have something called as isothermal process. What do you mean by isothermal process? I'm pretty sure that by now you already know it. Isothermal means the process that is carried out at constant temperature. What is it? Process carried out at constant temperature, isn't it? Carried out at constant temperature. Is that right? Yes. Very good. Very good. Absolutely great. Okay. Moving on to the next process. What do we have? Next we have isobaric process. Now what is isobaric process? You know, bar atmospheric pressure, 1 bar atmospheric pressure, isn't it? So that means the process that is carried out at constant pressure. Okay. What is isobaric process? Isobaric process is, but choose process that is carried out at constant pressure. Clear? Okay. All right. I could not write pressure completely. Please write it. Okay. You guys, please write it. Yeah. Ma'am is lazy, but you don't have to be, because you are appearing for JEE, not me. I'm done with that stage of my life. Now let's go to isochoric process. What is isochoric process? Pressure is done, temperature is done. Now what? Now what do we talk about? Volume, obviously, isn't it? Yes. So what is isochoric process? Write it. Isochoric process is, but choose process carried out at constant volume. And after all of these, now we come to the most important one, that is adiabatic process, isn't it? What do we talk about? We talk about adiabatic process. What is this adiabatic process? Simple. You all know we are going to talk about an isolated system here, isn't it? What is adiabatic process, everybody? The process in which there is no heat transfer between the system and the surrounding. Basically an isolated system which has an adiabatic wall, isn't it? Yes. What is it? Process in which there is no heat or energy exchange, between system and surrounding, between system. You know, if I keep saying system, I will start writing it as SYSTUM only, and then all of us will be called as supporter of Elvish Yadav. We do not want to be that, right? We do not want to be that. Achha, by the way, apart from all of these, you also have another process which is called as cyclic process. Okay. You also have another process that is called as cyclic process, Bachus. And what is the cyclic process? Any idea? In cyclic process, obviously what happens is the initial state and the final state are same. A process when initial state and the final state are same, right? Yes. Yes, and also if you look at the graph of a cyclic process, please do remember what I'm telling you right now, okay? I'm telling you something that is very important. Pay attention, everybody. Pay attention. What am I saying? I'm saying that in a cyclic process, if you look at the graph, you will see that there is always a loop that is formed. And that is the identification of a cyclic process. If there is no loop, then it's not a cyclic process. If there is no loop, it's not a cyclic process. Okay. For example, see, if I go from here to here like this and come back like this, what did I do? My initial and my final state are same, obviously, but right here I did not form a loop. I did not form a loop here. But now check it out. If I go from here like this, then if I go like this, then if I go like this, and then I come back here, now I formed a loop. So this, the later part is a cyclic process. The first one, when I just did left to right, this is not a cyclic process, everybody. Are you getting my point? Yes. So what is it? A process when initial and final state of the system, okay, of the system is same. That is called as a cyclic process. All right. Yes, everybody. Is this clear? Is this clear? Got it? Okay. And one final note that you may want to write is that the wall that separates system and surrounding, what is it called as? Adiabatic wall or dithermal wall. Okay. Depending on system to system. All right. Depending on system to system, it changes, isn't it? So let's write that down as well, just so that everything is right in your fingertips. Wall separating system and surrounding is called as dithermal wall or adiabatic wall, depending on system. All right. Yes, everybody. Cool. We will come to that, Mr. Friend. We haven't spoken about work done. No, that's why I'm not saying. Right now, understand the easy explanation. Okay. Understand the easy explanation. Work done and everything, we will come to that. Don't worry about it. We will come to that. Chill. Okay. Kritik Chaudhary, ma'am, you have changed so much. Is that so? How? Have I become fat? Have I become thin? What happened to me? I don't think so. I have changed. I'm still teaching you the same way. And I'm still your forever Nabamita Ma'am. Alright? Yes. Okay. Alright, guys. Now coming back to something called as state of a system. Okay. What is the state of a system? The state of a system says that there are state functions and there are path functions. So let's talk about that. Let's talk about the state functions and the path functions. Okay, what are the state functions and path function? What are these state functions and path function? Are you fine? Yeah, I am fine. Why? What happened to me learning soon? What happened to me? Nothing happened, no? Nothing happened to me. I'm fine only, Bachu. What happened to you? Am I not looking fine? Do I look sick? Am I looking sick? Anyway, guys, state functions, everybody. You know, state functions, what happens is, okay, let me give you an example, yeah. State function, for example, everybody. You clearing your JEE, yeah, you clearing your JEE is actually a state function. Nobody is actually going to ask you that, How did you clear it? I mean, yeah, obviously, like, people like us in Vedantu, we might ask you that what did you do? What was your journey and all of that. But otherwise, once you reach there, you are already successful, isn't it? No one is going to ask you. Correct? Yes, everybody, right? Or basically, or what else? What else can I give it to you as an example? Okay, I can't remember top of my head. No other example is coming up. So I think let me give you the scientific, the chemistry related state function. The chemistry related state functions are basically, the values that depend on the state of the system, and it does not depend on how you have reached there. Okay, how you have reached there, nobody talks about that, but you only talk about, are you successful, are you not, are you successful, are you not, right? Are you getting my point? Yes, everybody. For example, pressure, volume, temperature. Yes, pressure, volume, temperature. No one is going to ask you that, acha, how did you increase the temperature? You heated it like this, or what did you do? Did you do like this, or what did you do? No one is going to ask you, how did you get it? But everybody is just going to ask you, has it increased or not? That's it. Okay. So state functions are basically the values depend on the state of the system. Okay, what did I say? The values depend on the values depend on the simple definition of cyclic process. Bacha, is this not simple enough? Initial and final state of the system is same. As in, okay, as in physics. In physics, you know what is displacement, right? For example, if you start from, let's say you start from Bhopal, then you go to Guwahati, okay, then you go to Guwahati, then you go to Bangalore, all right, and from here, you again come back to Bhopal. This is a cyclic process. Getting my point? Learning soon. That is a cyclic process where you started from Bhopal, you came back to Bhopal and nowhere else, and you formed a loop as well. So this is your cyclic process. Got my point? Yes. But as we move ahead, you will learn about it. Don't worry. Okay, you will learn about it. Okay, how long is the lecture going to go on? What will you do knowing this? You sit and study. No, bachos, this will go on till at least 10:30. I'm guessing at least 10:30. It's a long process, and if you keep asking me these questions, then it might take longer. So shh and study. No breaks, no disturbances. Study, sit and study. I only want you to interact with me when you have a doubt. Okay? All right. So what is a state function? A state function is the values depend only on the state. Okay? Only on the state of the system. Only on the state of the system and not on how it is reached, and not on how it is reached. Clear? All right, now let me give you a trick. Have you all seen that Gibbs-Helmholtz equation? Everybody knows, right? Or Gibbs free energy. The difference in Gibbs free energy, bachos, what is the difference? The difference is always just a number, isn't it? It's just the magnitude. Nobody is going to ask you, how did you achieve the difference? How did you achieve the difference? No one is going to ask you. Also, now I found this thing. This thing. Path function. Yes. A lot of people, when they have lost a little bit of weight, right? When they have lost a little bit of weight, people also tell you about the journey, how I lost my weight. You know, I did this, I skipped meals, I did intermittent fasting, I worked out, I picked up some, weights and everything. So that is a path function. Losing your weight, how did you do it? When you tell the story to people, that's a path function, because everybody is interested. Oh my God, how did you do it? Oh my God, how did you do it? Oh my God, how did you do it? But currently, let's talk about your 12th grade. Your 12th class marks, everybody, your 12th class marks, how much do you need? You only need 75% criteria, right? Is anybody ever going to ask you, how did you achieve this much marks in class 12? Nobody. But how did you achieve a rank 1? How did you achieve rank 1 in your JEE? Everybody will be interested. The whole nation will be like, how much did you study? How many hours did you give it? What books did you study? Did you make notes, or did you follow this channel? Did you follow this institute? Did you follow that institute? See, it's a path function. Everybody is interested. How did you achieve? But your 12th grade marks, which is a 75% criteria, no one wants to know how did you get it. You got 75% criteria, you get admitted in your you get admitted in your dream college. So that is a state function. Now I got an example. Yes, are you guys understanding it? Yes. Or I can also say, in other words, I can also say that it depends on final and initial state. Okay, depends on final and initial state. So what are the examples that I gave you? The examples are pressure, volume, temperature, delta G, delta H, okay, delta S, okay, delta U, that is internal energy, and etc. Okay, all of these are your state function. Am I clear? Moving on from here, let's talk about path function. Let's just write it, everybody. I think I have explained you what is path function very clearly. What is path function, everyone? Functions that depend on the path taken to reach that specific value. All right. Functions that depend on the path taken to reach that specific value. For example, work, heat transfer. Yes, for example, you have work, you have heat transfer. All right, what do you have? You have what else do you have? I think that's it. That's it is enough. That's it. If you remember, I think it's enough. All right. Yes. Now we come to a point called as internal energy. But acha, before internal energy, let's learn about what is intensive and extensive properties. Okay. All right. Let's learn about that, because we will be needing that in when we are trying to understand this. When we are trying to understand internal energy. All right. Yes. Okay. Yes. Very good. Sabarmati, you're not gonna study, no? Not gonna pay attention? Huh? Not gonna pay attention? You want to know about my life story today, or shall we complete it? Study, no, bacha. Why are you playing with your own life? Huh? Why are you playing with your own life? Chalo, guys, let's understand extensive and intensive properties. And what are these, okay? Extensive and intensive properties. What are these extensive and intensive properties? So, first of all, let's talk about an extensive property. Okay, what is an extensive property? An extensive property is basically that whose value depends on the quantity or size of matter present in the system. What did I say? It depends on the quantity or size of the matter that is present in the system. For example, temperature. For example, pressure. For example, surface tension, vapor pressure, melting point, boiling point, viscosity. These are all extensive properties, everybody. Okay. These are all examples of extensive properties. So if I have to write, let's write it down that an extensive property is a property whose value depends on, yes, very good, Mayank, yes, whose value depends on the quantity, or size of matter present in the system. Clear? Example, what are the examples that I told you? Examples are temperature, pressure, viscosity, surface tension, tension. All right. Yes. Vapor pressure. Vapor pressure. Melting point, boiling point, and etc. Obviously, there are a lot more. Yes, now don't ask me in the chat box that, ma'am, what about this, ma'am? What about that, ma'am? What about this, ma'am? Don't ask me about each and every property that is present under the sun, okay? The rest of the things you are supposed to know. Now, let's talk about an intensive property. What is an intensive property? What is an intensive property, everybody? Does anybody know the definition here? What is an intensive property? Those properties which do not depend on the quantity or size. That's it. Yeah. That those property does not depend on the size or intensive. Yes, very good, very good. What are you writing? Temperature is intensive. Weight, volume, internal energy, Gibbs free energy, heat capacity. These are the one, okay? These are the one. Chill. An intensive property which do not. No, I will not speak in Hindi, bachu. The channel name is only Vedantu JEE English. This is an English channel, completely English channel. I have to teach you in English, okay? Okay. Which do not depend on the quantity. On the quantity or size of matter Did I write it wrong? Yeah. What happened? Did I write it wrong? Give me a minute. Let me write down the definition. Don't confuse me right now. Let me write the definition. Then we will go back and we will check it out. Okay. Or size of matter present are known as intensive properties. Okay. All right, everybody. Yes. Chalo. You are saying that you have figured it out and I have written it wrong. Extensive properties. Chalo, let's check it out. Let's check it out. Temperature, refractive index, melting point. Yeah. I think I have. No. I think what I've done is. Wait a second. I have written it ulta. I've written it ulta. Sorry. No. You're right. Yes. Weight is extensive property. Okay. Weight is extensive property. No. Weight is extensive property, bachu. Weight is extensive property. Weight is extensive property, okay? Weight is extensive property, right? Then volume is extensive property, right? Entropy is extensive property, right? Yeah. I wrote ulta. Yes. Example. And here the examples are temperature. I was also thinking that how come melting point and boiling point? Because we know that melting point of water is forever the same, isn't it? So melting point, boiling point, right? Melting point, boiling point, temperature, I have already written. Pressure, surface tension, right? Surface tension. Viscosity. These are all intensive properties, okay? These are all intensive properties, and the extensive properties are weight, volume, internal energy, entropy, Gibbs free energy, heat capacity we will learn about right now. Heat capacity, okay? Heat capacity, enthalpy, right? Gibbs free energy. These are all extensive. All right, everybody, this is clear? This is clear? Yeah, is this clear? Yeah. Yeah, everybody. Yes, this is clear. Okay, all right. Okay, ulta means opposite. What I did was I mixed and matched. So extensive properties examples are weight, volume, entropy. Just before this, what I had done was I wrote the intensive property examples as a part of extensive property, and I wrote the extensive property examples as intensive property. Okay. All right, everybody. Understood, guys? Is this clear? Yeah. Okay. Moving on. Now, what do we have to study? Now, we are going to study about something called as internal energy. Okay. We have to study about something called as internal energy. Everybody ready? Yes, everybody. Are you all ready? But before that, let's do an example here. Chalo, let's do a question here, guys. Let's do a question here. Are you all here? Are Baba Kamal, write down. Yeah, there are a lot of examples. I can't sit and keep writing everything, right? I can't sit and write each and every property of matter. So there are a lot of them, but now you understand, right? Now you understand what I'm saying, right? You get the concept, isn't it? That's it. Okay. All right. So tell me the question, everybody. Tell me the answer of the question. Which of the following are state functions? Which of the following are state functions, everybody? Go ahead, let me know. Go ahead, let me know the answer, everyone. Let's see who can answer. Let's see who can answer, everyone. Come on. Somebody is saying A, somebody is saying C, somebody is saying A. Guys, the answer is, I just told you that Q and W. Q and W are definitely not state functions, but Q plus W and H minus TS. H minus TS is basically what? Delta G is equal to delta H minus T delta S, isn't it? So, Gibbs free energy is a state function. So yes, the answer is correct. Option A is the correct answer. Very good. Yes, option A is the correct answer. All right. Yes, everybody, is this clear? Acha, is there something that I have missed out on? Is there something that I've missed out on? Acha, ha. Okay, here is something. Here is a trick. Here is a trick, by the way. Let me tell you that if there is a ratio, the ratio of extensive, okay, the ratio of extensive property and another extensive property, if there are two extensive properties and if you divide one by one, okay, then what will happen is you will get an intensive property, okay. So extensive property, extensive by extensive is always going to be intensive. All right, intensive. And by chance, if you do not know how to figure it out, always know that if you get these words like specific heat capacity, molar heat capacity, then it is always going to be intensive. Okay, intensive bole to molar heat capacity, specific heat capacity, or any time you get this word, just know that these are all intensive. Okay, these are all intensive. Great. Okay. Now we go to internal energy. So what is internal energy, everybody? As you all can see that the definition is written right here on the board, isn't it? The definition is right here on the board. What is internal energy? Internal energy is basically the energy that is contained within the thermodynamic system. Within the thermodynamic system, the energy that is contained, that is your internal energy. Bole to, whatever energies that you see, right? Whatever energies that you see, for example, you will be seeing some kinetic energy, you will be seeing some potential energy, isn't it? All of these, etc. This is the sum of all the energies that a thermodynamic system has is your internal energy. All right. Yes. Yes. The sum of kinetic energy, potential energy, etc. The sum of all energies. The sum of all energies is basically your internal energies. Is this clear? Is this clear? Now what am I saying? Yes. See, this is what is written. Kinetic energy bole to there is translational energy, there is rotational energy, there is vibrational energy, isn't it? Then there is electronic energy, there is nuclear energy, all of that together, the sum of all the energies that you have in a thermodynamic system, that is your internal energy. Okay, we will come to this mathematical derivation a little later because I will come to that. I will show you how to get there. Okay, it is an extensive property. Now, do you understand why I taught you extensive property before internal energy? Because internal energy is an extensive property. So, if we have to go back here, then do you see here that extensive property, what is it? Internal energy is an extensive property. We can write this also as an example here. Are we getting my point, everybody? Yes. All right. Now let's understand some more things. Okay. What happens is this internal energy, it depends on the quantity of a substance. Why? Because it is an extensive property. Just told you, right? It depends on the quantity of a substance, right? Depends on quantity, of a substance. Okay, depends on quantity of a substance. Understood, everybody? Great. Now understand this. This is very important point, everybody. The absolute value of the internal energy, it cannot be determined. The absolute value of internal energy, it cannot be determined. But what you can calculate is, remember what did I tell you? Delta G, delta U, delta H, all of these if you see, that means what is it going to be? Very similarly, here also you will see that you can calculate the change in internal energy, bacha. You can calculate the change in internal energy, but you will not be able to calculate the absolute value of internal energy. All right. So what did I say? This is very important. So writing it down in white. Absolute value of internal energy cannot be determined, but the change we can calculate. But the change in internal energy can be calculated. All right, this is clear, everybody? Yes? Okay. Now, delta, this internal energy, how is it denoted? How do you denote this internal energy, right? How do you denote internal energy? U. Internal energy is denoted by U or E. Is denoted by U or capital E. Okay. How do you denote it? You denote it by U or capital E. Okay. So this may change, right? The internal energy of the system may change when? When do you think that the internal energy of the system will change? When do you think that this U or this E will change? There are 3 times when it may change. Or there are 2 times. Actually, there are 2 times here. Okay. What are the 2 or 3 times that it changes? So, the internal energy, let's write it down. The internal energy, there are 3, yes. The internal energy of the system may change when matter enters or leaves the system, right? Yes. Or heat passes into the system or out of the system, or work is done in or by the system. So let's write it down. Work done on or by the system. Okay. All right. What is the other thing that I said? Matter enters or leaves the system. Matter enters or leaves the system. Yes. And finally, what happens is heat passes into or out of the system. Am I clear, guys? Yes. However, you have to understand, everybody, that the total energy of the system will remain constant. Yes, what did I say? The total energy of the system will remain constant. Please pay attention. Total energy total energy of system is constant. Cool. Yes, the total energy of the system is constant. Why? Obviously, no. Where will energy go? Haven't you heard about it from that? This will actually bring you to the first law of thermodynamics, and you will see. Hold on to your thought. The answer to the question, why is total energy of the system constant, that you will come back in some time. In some time you will see, okay? In some time you will see, okay? All right, chalo guys. Now you have to understand that if energy is released by the system, yes, if the energy is released by the system, then what are you going to say? You're going to say that delta U is negative. All right. Why? Because, okay, this is the system, right? This is the system. From this system, some of the energy is going. So what will happen? For this system, the energy is lost. The system has lost some energy. So delta U is going to be negative. But if the system absorbs some energy, then what do I say? Then I say that delta U is positive. Then what do I say? Delta U is positive. But now tell me, if I ask you, what about isothermal process? For isothermal process, what will happen to delta U? Is it going to be negative or positive? Arey baba, delta U is going to be zero, na? Isothermal, constant temperature, delta U is going to be zero. Understanding? Yes, very good. Okay, so let's write that down. Whatever I just spoke to you. Whatever I just spoke to you, let's write that down. What are the things that I said? I said that, first of all, for isothermal process, delta U is 0. Delta U is equal to 0, right? Yes. Then I said that if energy is released by system, if energy is released by system, then what will happen? Delta U is negative. Yes, delta U is going to be negative. But if energy is absorbed by system, if energy is absorbed by system, then what happens? Delta U is positive. Is this clear, everybody? Is this much clear, guys? Yes. Any doubt till here? Any doubt till here, or are we all clear with everything, everybody? Are we all clear with everything, guys? Yes or no? Yes or no? Okay. All right. Everybody is understanding. Looks like that. Yes. Everybody is understanding. Am I not moving? Am I not moving? Oh yeah, I am moving. I thought that there was an issue. Chalo. All right. Acha. Clear hai? If I sit, then who is going to take the class, huh? I will be. Acha, bachos, for those of you who are complaining that, ma'am, you can't see anything, read it. Chalo. I'll move aside. Read it for a while. Read it, read it, read it. Read it. Yes. Read everything. Then I will move forward. We have to do internal energy change by work, internal energy change by heat transfer. Then there is something called as pressure volume work. We will read about all of that. Yes. Thank you, Moni. Thank you so much. Chalo. Everybody, you have read. Don't worry about it. Even if you are not able to see certain things, it's okay, because I send you this whole PDF to the Telegram channel. So just join the Telegram channel. I'll be sending you the PDF there, and you can read this whole thing, whatever I have written. Throughout the whole session, whatever I have written, you will be able to see all of these things, okay? Don't worry. Chalo. Alright, everybody. Now, let's read about internal energy change by work. What are we going to read about? Internal energy change by work, okay? Internal energy change Okay, all right. Our third part is not included. I will include. Don't worry. Chill. No, study what I'm teaching. No, you guys have to just, you have to talk about everything else. Be the system, not the surrounding. If you're the surrounding, then JEE will be cancelled. Be the system. I'm teaching you something now, so be a part of the system. Telegram link is in the description box, bacha. In the description box. Right below this, you will be able to see. Okay? Okay. So, in this case, when we are talking about this internal change by work, right? By work. Why are we saying that internal change, when we are saying that internal energy change by work, that means that matter is not getting exchanged. That means that energy is not getting exchanged, right? Matter and energy is not getting exchanged, but internal energy I have to change. So how is that possible? Of course, work. And that means that what is my system? My system is going to be an adiabatic system. Makes sense or nonsense, everybody? What I'm saying, does it make sense, everyone? Great. So coming back to it. So when I am talking about an internal energy change by work, that means we are going to speak about, okay? That means we are going to talk about an adiabatic system. Yes? Because I just told you, right? What are the different ways of changing internal energy? The different ways of changing internal energy is basically work done on the system, matter enters or leaves the system, heat passes into. Both of this cannot happen. We're talking about only work done. That means that, okay? That means that it has to be an adiabatic system. Hey, Anubhav Soni, you can't read also. That means you are not a good student. Can I tell you the same thing? Can't you read? What is the channel name? Vedantu JEE English channel. Can you see that? Huh? Just like that you will come and spam, no? Just like that you will come and spam. Can't you see what is the channel name? Vedantu JEE English channel. You want to read in Hindi? Go learn in some other channel. Just like that coming and chumma spamming. Anyway. Alright. So what are we going to talk about? Adiabatic system. Let's write that down. Adiabatic system. Yes. So what is happening in an adiabatic system? What is happening in an adiabatic system right here? Like we have just told, like we have written, the heading says that by work. So either we can do some mechanical work, right? Either we can do some mechanical work, like we must do some work and change it, or there can also be electrical work, right? There can also be an electrical work. Now, when I say that mechanical work, so I understand that this is an isolated system, right? What I have is an, okay, let me draw the diagram, everybody. Okay, let me draw the diagram. Let's say that this is my isolated system. Okay, this is my isolated system where what is happening here is the matter and the energy are inside. Matter and energy are inside. These things, they cannot get exchanged with the surrounding, right? The matter and the energy, they cannot get exchanged, isn't it? And Q is equal to 0. Q is equal to 0, right? Why? Adiabatic wall does not allow the transfer of energy, right? The adiabatic wall, it will not allow the transfer of energy. Yes, but allows as work. This is an isolated system. It does not allow transfer of heat and work, isn't it? So that means everybody, that means what can I do? I can do two things here. I can do two things. One, by mechanical work. And what is this mechanical work, bachos? Don't you think that I can just dip a stirrer here? Can I use a stirrer which just it rotates it? And that way what will happen? There will be, a lot of collision that will be happening, and so what will happen? The internal energy will increase. Am I right, everybody? Is it making sense? Is it making sense? Can I not use a stirrer? If I use a stirrer, then what will happen? It will go like this and the internal energy will change, isn't it? Yes. Very good. Absolutely great. Absolutely great. Yes. Well done. Now, by electrical work, right? What did I say? The second thing is by electrical work. How can I use electrical work? Have you seen in your house that you have a geyser or you have something called as in the geyser, I don't know if you have touched the geyser, but I haven't. But I'm guessing that the geyser does not really get hot from the outside, isn't it? Yeah. The geyser does not really get hot from the outside. And also for some time, what happens is for some time, the water remains hot, isn't it? Yes. Or have you seen an immersion rod? Have you seen an immersion rod where you have those gul like this, a rod that you dip inside and the water gets heated up? Yeah. So these two things you can use. These two things you can use and you can increase the internal energy. And in both the cases, my dear students, the change in the state of system is the same, irrespective of the path that you have taken. Either you take the mechanical work path done or you take electrical work. In both of these cases, you will see that the change in the state of the system is same. Because at the end of the day, what are you trying to do? You are just trying to increase the internal energy. Nobody cares what you are using. You are using electricity? Great. You are using mechanical work? Great. Getting my point? Yes. So let's write that down. Let's write that down that in both the cases, everybody, yes, what is happening in both the cases, change in state of system. Change in state of system is the same, yes, is the same, irrespective of the path taken to change the state. Is this clear, guys? Is this clear, everybody? Yes? Is this clear? Okay, taking a little break. Now my voice has started to pain. Now my voice has started to change. Yes, Kamal, you are right. Yes, can you upload videos about VIT Triple E? Yes, I will. Yes, animal lover. What happened? What is your doubt? Tell me. Whew, okay. All right, guys. Next. Let's talk about internal energy change by heat, right? Internal energy change by heat. Internal energy change by heat. Achha. Here what is happening is internal energy is getting changed, but this time heat. Yes. So here what is happening is internal energy, the system may change. Yes, the internal energy of the system may change when work is done on or by the system. Heat passes into or out of the system. These are the two things that we have understood, isn't it? Yes. These are the two things that we have three things that we have studied, right? Yes, work done, heat passes, or matter exchange. Correct? Or matter exchange. But here what are we saying? Here we are saying that delta U is equal to Q. What is Q? Q is the heat transferred due to difference in energy. What is Q? Q is the heat transferred. Q is the heat. Baba Re, what is this? Q is the heat transferred due to difference in energy. Okay? Due to difference in energy. Clear? All right. Now, what if this time the system releases some heat to the surrounding? Then what will happen to Q? What will be the value of Q? Q will be negative, isn't it? Yes, because the system is doing the work. The system is releasing the heat, so system is losing some heat, so Q will be negative. But if now the surrounding gives some heat to the system and the system is absorbing some heat, then what will happen? The heat, the temperature, the heat is getting increased for the system, and this time the heat is going to be, Q is going to be positive. So let's just write that down, whatever I have told you right now. Okay, what have I told you? I have told you that Q is negative. Q is negative when heat is transferred. Okay, Q is negative when heat is transferred from system to the surroundings. Okay, and Q is positive. Q is positive. Everybody, yes, you guys are doing a great job. Keep answering. Q is positive when heat is transferred. Heat is transferred from from surrounding to the system. Clear, everybody? Yes? Clear? Very good. Very good. Now, internal change by heat and work. Okay. Let's take a look at this. Internal energy change by heat and work, by both. Okay. By both. Let's take a look at this. Okay. I'll have to increase some pages, guys. Just a minute. Yeah. Just a minute. Give me a minute. Give me a minute. Give me a minute. Yeah. I will have to increase some more pages. I need to write more things down. Yeah. Just a second. Chalo, just in case. Let's add it. All right. Yes. What is it that I was telling you? Yes. What is it that I was telling you? I was telling you internal energy change by heat and work, isn't it? Okay. Internal energy change by heat and work, bachos. What does this mean? Now, this means, everybody, this means that very easily you can write it delta U is equal to Q plus W, everybody. Yes, delta U is equal to Q plus W, isn't it? And we all know that delta U right here is a state function, isn't it? This, my dear students, is a state function, and I think you all will agree with me when I say that Q plus W is a path function, isn't it? And this, my dear students, okay, this, my dear student, is the first law of thermodynamics. What is this? This is your first law of thermodynamics. What is it? It says that the energy of an isolated system is constant. The energy of an isolated system is constant. That is law of conservation of energy. Or everybody, I think from a very young age you all have learned, isn't it, that energy cannot be transferred or it cannot be destroyed, but it can only get transferred from one place to another. Haven't you read about it? Haven't you read about it? Yes, no, I'm not erasing the PDF. The PDF is right there. PDF is right there. I was just increasing some more pages, right? Yeah. So this, my dear students, this right here is your first law of thermodynamics, but don't worry, we are going to talk about it a little more, okay? We are going to talk about it a little more. So this basically says that the energy of an isolated system, okay? The energy of an isolated system, all right? Of an isolated system is constant. Clear? All right, everybody? Yes. Now, the last one. This is a little more important, everybody. Okay. This is a little more important. Okay. All right, everybody. Please check it out. Please check it out, everybody. What is this? Now we're going to talk about internal energy change by pressure, volume, work. What is it that we're going to talk about? Delta U, that is internal energy change by pressure, volume work. And this will introduce us to reversible and irreversible process very soon. But let's understand this, okay? So what we are talking about right here is work can cause a change in internal energy of the system, right? We know this, isn't it? And pressure or volume work done is also work done by expansion of gas, right? If the gas expands, okay. For this, we have this, everybody. For this, understand. Ajit, bro, what will you do? What will you do if I'm married or if I'm not married? What will you do? Janavi, I will not be repeating it. If you want me to repeat it, what you can do is just go back and watch it again. You will be able to understand everything. Okay? Alright? Yeah? What will you do, Ajit? If I am, what? If I am not, what? Why do you want me to tell you this? Why can't you focus on what I'm teaching you right now? Okay, everybody. So let's say that we have a piston here, right? We have a syringe here. Okay, syringe. You must have all seen it. You must have all seen it, right? So let's say that this is where it is. Okay, the piston is right here. But what if, imagine the gas starts to expand, and let's just say that, okay, everybody, can you see this readings? Yeah, can you see this readings here? Do you see that here what is written? Let's say that there is 0.1, it is written, isn't it? This is 0.1 that is written. Now let's say that the gas that is inside this place, okay, the gas that is right here, this starts to expand, okay. If this starts to expand, then what will happen? This will move beyond, the piston will move like this, right? And what if by chance what happens is the external pressure is more, okay? See, for example, my finger right here, this is the external pressure. This external pressure is more, so what is happening? The piston is moving inside. Yes, the piston is moving inside, isn't it? Yes, the piston is moving inside. So, even if you look at your NCERT book, you will find this image, isn't it? You will find this image. So, let's say that the piston is here and then it moves from here to here, okay? Let's say that it moves from here to here. So what is the volume change? The volume change is obviously the length into area of the cross section, isn't it? Length into area of the cross section. And what is the P here? What is the P here? What is the P here? Force divided by area. That is your P, isn't it? Force divided by area. That is the P, isn't it? Very good, everybody. Very, very, very good. Yes. So you guys are understanding. So let's write it down here. So let's say that if I draw this diagram, okay. Let's say that I am going to draw this diagram here, okay? Here, everybody, here. Like this. Let's say, okay? Drawing it. Check it out. Okay? This is the piston here. So, let's say that this right here is my piston. The piston moves from here to here, okay? The yellow color part is where it moves, okay? The yellow color part is where it moves. So, from here to here, let's just call this, okay? Let's just call this L. Yeah, can we say that? So that means that what is the volume change, everybody? What is the volume change? The volume change is equal to delta V is equal to L into A. Yes, or it is basically V final minus V initial, right? And what is P? Pressure is always equal to force divided by area. Isn't it something that we already know? We do know this, right? Now the question that comes is, what is the force on piston? What is the force on piston, my dear students? The force on piston is equal to pressure into area. Yes. And that means that I just showed you that when I pressed it, what happened? It was P external, isn't it? It was the external pressure. So can I write it as P external multiplied with A? I can. Isn't it? Yes. Isn't it? Now, here, what will be work done? Here, what will be work done, everybody? Work done will be equal to F into L, or it can be called as P external multiplied with area into length. Right? Right? And what is A into L? What is A into L? Everybody, we saw it right here. That is delta V. That is delta V, everybody, isn't it? Isn't it delta V we have just seen? So that means that this is P external multiplied with delta V. Yes, delta V. Now we saw that this was contraction when P external was, when I have applied the force, when P external was more, what happened? There was compression that happened. Yes, because it decreased. So delta V is going to be negative. Why? Because decrease. Because decrease of volume happened, isn't it? Because decrease in volume happened. Am I right, everybody? Because decrease in volume happened, right? Very good. Very good. Very good, everybody. Yes. So that means that, that means that I will have to write it as P dot EX, okay? PEX, P external basically. P external minus delta V, right? Minus delta V. Why? Because compression happened, right? Because decrease in volume happened, correct? Very good. Very good. Okay. Now, if I say that if there is decrease in volume, that means my work is also going to be negative. Work is also going to be negative. But I can clearly see that the work done is on the system. The work done is on the system, and if work done is on the system, that means that this has to be positive, right? I saw that P external was more, so work done is on the system, correct? Work done on the system, that means that this has to be positive. Work done on the system, correct? Now, if W is positive, bachus, if W has to be positive, that means that I will have to add the negative sign here. Now, minus and minus, right? Now, minus, negative is going to give me positive, isn't it? Negative is going to give me positive. So, for work done to be positive, P external is also going to be negative. Understood, everybody? Yes. And by chance, if W is equal to minus P delta V, if W is minus P delta V, this means compression. This means compression. And if both of these are, or basically, or both of these, or let's say that minus W is equal to P delta V, this means that expansion. This means expansion. Is this clear, everybody? Is this clear, everyone? Yes. Is this clear, everybody? Yes, guys, or no? Clear hai? Great. Acha. Now, all this while, when I was teaching you this, okay, check it out, everybody. Okay, let's say that the piston is right here at the end, right? Right here at the end. So, there are two ways that I can bring it till here, right? There are two ways. I can either go tuck like this. This was one single step, right? This was one single step and I brought the piston right back. Or what I can do is I can slowly bring it like this. I can do it like this, like this, like this, like this, like this, isn't it? Then I can bring it. Yes. So that means that there is a possibility of a single step change or there can be a gradual change, isn't it? Yes. There can be a single step change or there can be a gradual change. For example, you know, right now I'm teaching you what? Right now I'm teaching you a one shot. Right now I'm teaching you thermodynamics in one shot. That means one single class and everything will be done, right? But if I have to take you through like, you know, many small sessions of this thermodynamics, then what will you do? Integration. Isn't it? You will do integration. Very similarly, right here also we will do the same thing. Okay. So for example, if I have a single step change, okay. If I have a single step change versus what do I have? Gradual change. Gradual change, right? So what do you do, everybody? For a single step change, what you will write is W is equal to, let's just say that, you know, if it is single step is easy, right? Single step is what? Single step is just P delta V. Single step is just P delta V, right? Single step is P delta V. But if there are small change, then it will be summation of P delta V. If I take you through, even smaller, half an hour session of thermodynamics every day, that will take me endless amount of days, isn't it? I will require at least 20 to 25 days to be able to complete it, isn't it? So instead of summation, then we will have to use what? Then we will have to use integration. Summation is for still quantitative. Like, you know, you can still maybe add it up. But what if it is infinite? If I take it for 20-25 days, you will be like, oh ma'am, till how many days will you do thermodynamics? We can't do it. Then you will have to do integration, isn't it? Understood, everybody? So then it will be equal to minus integration. Why did I write minus here? This will be VI to VF, then P external dV. So instead of delta V, you will write dV, isn't it? Yes. All right. Got it? Clear? Acha. Now we come to something called as types of process, that is reversible and irreversible process, right? What is reversible and irreversible process? So you know what we have seen in nature? We have seen that something that goes through gradual change, that is a reversible process, and something that goes through an single step, that is your irreversible process. Most of the time, right? Most of the time. For example, birthday balloon and boom, it got torn into numerous pieces. Will you be able to stick it back? That's an irreversible process. That is something that you have learned from a very, very, very young age, isn't it? And what is reversible process? You know what is reversible process, isn't it? Yes. A reversible process is like your hair growing and then it again gets cut, right? So this is a gradual change. Your hair growing your hair. Like look at me, I have cut my hair, now I want to grow it back. It's not growing only. That's another sad thing in my life. It's not growing only. So this reversible process is a gradual change. It doesn't happen in a one day. It does not happen in a one day, isn't it? Are you getting my point? Yes, everybody. So great. Okay. So let's talk about the reversible process. Okay. Let's talk about. No, Bachu, I'm a Bengali person. I'm not a Telugu person. In fact, I'm not a person only, I think, sometimes. Let's talk about reversible process. Okay. Reversible process is usually gradual change. Okay. Reversible process is a gradual change usually. An irreversible process we see is single step change. Okay. Single step change. Julio? Yes? Yes. Very good. Very good. Okay. Now, if we want to relate work done in reversible process with pressure, what do you do? What do you do? If we want to relate, okay, let's say that relate work done in reversible process with pressure. What will you do? Very simple, very easy. We have just done it. No, what will you do? You will write here work that is reversible is equal to integration. Yes. How will you integrate? V1 to V2, and you know that P external multiplied with dV, isn't it? But what will happen here is, do you understand that there will be P plus minus dP that I have to write, and here I will write dV, right? But what if the pressure difference is very small? If the pressure difference is very small, then dP multiplied with dV. Everybody understand this. Everybody check it out. Please check it out. If dP is multiplied with dV, okay? Everybody. Okay, here we go guys. Here we go. If dP multiplied with dV, okay? If dP and dV are multiplied and dP is a very, very, very small quantity. If dP is a very, very, very small quantity, then what do? It is so small, then poof, poof, take it away. You don't even have to add it, right? Yes, you don't even have to add it, isn't it? Yes, you don't have to add it. Exactly. So what will you do? You will write minus integration P dV. That's it. That's it. Yep. All right. Yes. Clear? Clear or not clear, guys? Are you understanding? dP multiplied with dV is so small that poof, make it fly away. Let it fly away. That's it. Okay. Acha, now you must have heard about this ideal gas equation, right? We have heard about something called as ideal gas equation in our previous sessions also, isn't it? Yes? Yes? Yeah, sure, Divyakant. You wish whatever is important for you. I have nothing to say. If Dandiya is right now more important for you, please go ahead. I have nothing to tell you. Please go ahead. No worries. No worries, Bachu. Dandiya is more important for you. Sure. Go ahead. Absolutely. I'm fine with it. I'm not gonna ask you not to. Yeah, Gannu is telling me exactly. PV is equal to nRT is something that we have read, isn't it? So let's bring that. Let's bring that. So what do we have? We have ideal gas equation. What is our ideal gas equation? Minus P is equal to, let's say, nRTY minus P. Am I writing? Let's not write minus here. nRT by V, right? nRT by V. PV is equal to nRT. So P is equal to nRT by V. Correct? So now if I use that same work done in a reversible process, what will happen? What will happen to my work done in reversible process? Let's write it down. REV is equal to minus integration V1 to V2. Yes, nRT divided by V dV. Clear? No, integration you all know, right? Integration you all know, isn't it? So how do we do it? Now what are we going to do? This nRT, all constant, bring it out. nRT, all constant, bring it out. So what will we do? We will write it as minus nRT integration V1 to V2, 1 divided by V multiplied with dV. Isn't it? Yes. Great. Now what is the property here, everybody? What is the property, guys? I hope that you all are, yes, I hope that you all are absolutely clear with the integration and all. I can't teach you. I'm very bad at mathematics. If you want to learn from me, you will definitely not be able to clear. So don't ask me. I know very basic mathematics that is required here. If you want to know about integration properties, please go and ask Puneet sir when he's out of the hospital. Okay. So let's do this, everybody. That means this will be minus nRT ln of V here, V1 to V2. Right, everybody? Great. Now, what is the property of log nRT ln of V2 minus ln of V1? Very good. You guys know it. Kamal and Deepti, very good. Okay. Now, what do we have here? This means that minus nRT ln of V2 divided by V1. Is that right? Yes. Now, if I have to change this ln to log, what do I do? Minus 2.303 nRT log V2 divided by V1. Correct? Yes, everybody. And if that is the case, bachos, if that is the case, so what does my actual equation become? My actual equation now becomes, everybody, look at this. This is important. Work done in a reversible process is equal to minus 2.303 nRT log V2 divided by V1. This is important. Write it down. This is important. Write it down. Asha, now tell me something. A reversible expansion will require more work than irreversible expansion. See, okay, understand it this way. When I'm taking a one shot, in one day with 4 hours or 3 hours, you guys have made a note of the whole chapter, isn't it? You guys are done with the whole chapter. But if I start taking half an hour session every single day I'm taking half an hour session. So you have to block your calendar every single day. If you are going out somewhere, then you have to come back and make the notes, right? You cannot go out at that single point of time. Any day or every day, you will have to wait from the very beginning that, oh, ma'am is going to take class. Oh, ma'am is going to take class. Don't you think that is more of a work? Isn't it more of a work that every single day you just study for half an hour? It's very annoying, isn't it? Because every single day you will have to wait for ma'am's class. And then if you want to start a new chapter also, you can't even, how many pages do you need? You will have to count down the pages, then you have to leave it, then you have to write down. You can't even start a new chapter, right? But today, once you are done with thermodynamics, you can start with a new chapter from tomorrow, isn't it? So don't you think that a reversible expansion will require more work than an irreversible expansion? Am I right or wrong? Am I right or wrong, everybody? Are you guys understanding what I'm trying to say? Yes? Are you guys understanding what I'm trying to say? Yes? So let me just write it down here that a reversible process, a reversible expansion will require more work than irreversible process. Correct? Yes, everybody? Great. So all this while, have we understood what is the difference between reversible and irreversible? Yes. Have we understood? Do you want me to write it down once again? What is reversible and what is irreversible? I hope you have understood, or should I still write it down, guys? Chalo, let me write it down only. Here. Let's write it down, okay? Reversible, and this side let's write irreversible. Okay, all right. So first of all, what happens in case of reversible? Acha, by the way, in nature, everyone, in nature, we do not see reversible processes. Okay, in nature, we hardly see reversible processes. Most of the time, we see irreversible processes. Okay, most of the time, we see irreversible processes. So first of all, what can I write here? I can write that this is imaginary. This is imaginary, all right, and this is natural process. Okay, this is natural process, all right. Yes, the system here is always in equilibrium, all right, and equilibrium that side. Acha, chalo, let's write it down one by one. Okay, let's write it down one by one. System here is always in equilibrium. System is always in equilibrium, all right. Yes, and here what happens is equilibrium exists only in beginning and at the end. What happens? Equilibrium exists only in the beginning and at the end. Cool. All right, everybody. Yes. Okay. Moving on. Moving on. Next, what do we know? Work obtained is maximum here. We have just calculated, isn't it? Work obtained is maximum here. All right. Here what is happening? Work done is minimum, right? Work is minimum. Right? Yes. All right. Okay. Next, it follows a reversible path. I mean, obviously, follows reversible path and takes infinite time. Okay. Follows reversible path and takes infinite time. All right. And here what can I write? Here I can write it follows irreversible path and finite path and finite path. All right, guys, this is the whole thing. Okay, come on, chalo. Read it, everybody. Read it once. Read it, guys. Quickly read it. Till then, I'm going to drink some water and take a little rest. Then we will start. Okay. Then we will start. Once you are done, please let me know. Are you guys done? Okay. Now, thank you, Pritin. Acha, now bachus, we spoke about this, right? We spoke about this, isn't it? Yeah. If you all remember, here what was happening was P external. P external. P external was more than the pressure inside. That's why I could do tuck and bring it in, isn't it? What if What if the expansion of gas, let's consider this to be a vacuum. What if the P external is going to be 0? What if P external is 0? Then what, everybody? Let's write it down, everyone. Let's write it down here. Work done in free expansion of gas. Okay. Work done in free expansion of gas. Have you guys noted it down, or shall I just give you a little bit time, everyone? Maybe I can also go and sit because my back has started to pain. Should I give you a little bit of time? Can we take a 5 minutes break, everybody? Screenshot is completed. Can I take a 5 minutes break, or can we take like a, let's take 2 minutes. Chalo, 2 minutes. I will also go and sit down a little bit, okay? I will also go and sit down a little bit. I need to sit down for a while. Yeah? Can we do that? 2 minutes, guys. Washroom, sitting break. Okay, for me. Back is paining now. Back is paining a little bit. So, 2 to 5 minutes. Cool? 2 to 5 minutes, everybody. Chalo. I'll see you in some time. I'll see you in some time, okay? Hello guys, I'm back. Quickly go and call up your friends. Thank you, Janavi. Thank you so much. Divya left, huh? Hey, GOC part 3 will come, yeah. You guys will do GOC, GOC, GOC. I will take GOC, yeah. Don't worry about it. I will take GOC. Don't worry. Chalo, guys, shall we? Quickly go and call up your friends, everybody. Jawbreaker, Kamal, Kurinai, Mithun, Simran, everybody, are you all here? Quickly go and call up your friends, everyone. Quickly, quickly, quickly. Chalo, let's start. Till the time all the other students are coming, I'm going to write down the heading, okay? Ah, you are all here. Thank you so much. Okay. So now we have to talk about, everybody what? Work done in free expansion of gas, okay? Work done in free expansion of gas, okay? Free expansion of gas bole to, that means the gas is going to expand and there is nobody to stop, right? The gas is going to expand and nobody is going to stop. That means that pressure, external pressure has to be zero, right? And external pressure zero means vacuum. When is it going to be external pressure zero? Obviously when there is nobody else, no one else, no molecules outside, no atoms outside. So what are we saying? We are saying that pressure external is equal to zero. And if external pressure is equal to zero, what did we learn? We learned that reversible work done is equal to P external multiplied with delta V. So P external is zero. That means what is work done? Work done is also going to be zero, isn't it? Work done is also going to be zero. Make sense or nonsense, everybody? Tell me. Work done is also going to be zero, correct? Yes. Why I said that? Because you know that work done is equal to minus P external multiplied with delta V. If this is equal to 0, then anything multiplied with 0 is what? 0 only, na? 0 only, na? So 0. Kiran, this is for everything, bacha. You want to give it for your boards. I am going to cover your NCERT. I am covering it for JEE Mains. I am covering it for JEE Advanced as well. So don't worry about it. Just sit here, study, and you will be able to clear everything. Your boards, your JEE Mains, your JEE Advanced. One lecture is enough. This is the only lecture that you have to watch and everything will be done. Okay. All right, everybody. Achha, so now if we get back to the first law of thermodynamics, which we still haven't been there, we will. This is just a part of this. After this, we also have to do graphs. Okay, we also have to do graphs. Okay. Achha, so now first law of thermodynamics. Sometime back only we have spoken about it, isn't it? What was the first law, everybody? Yes. What was the first law? What was the first law? We spoke about it that delta U is equal to Q plus W. Isn't it? Yes. And if W right here is equal to 0, then can I write that delta U is equal to Q? Yes, but this will have to happen at constant volume, correct? This will have to happen at constant volume, isn't it, everybody? Yes, yes, am I right? Acha, now I'm going to write here certain things this side, okay? I'm going to write here certain things. So please pay attention, everybody. Please pay attention. All right, yes. Please pay attention. What did I say here? What did I say? That delta U. What do you mean by delta U? Delta U is equal to U2 minus U1, isn't it? So U2 minus U1 is equal to Q plus W. Am I right? In this case, what is U1? U1 is your internal energy. U1 is your internal energy, my dear students. Am I right? Yes. What is U2? U2 is internal energy at final state. Internal energy at final state. Clear? Oh, this is that initial state. This is that initial state. This is that final state. What is Q? Q is amount of heat given. Amount of heat given. Amount of heat given. Am I right? Yes. And what is W, everybody? W is work done. Amount of work done. Clear? amount of work done. Is this clear, everybody? Yes. Okay. Acha, now, everybody, can you all tell me that what will happen to delta U if it is an isothermal system? For an isothermal change, what will happen to delta U? Don't you think that delta U is going to be 0 for an isothermal change? Yes. Delta U is going to be equal to 0 for isothermal change. Why? Because Q, what is Q? Q is amount of heat given, baba. But isothermal, there is no heat given, there is no heat taken. So, what is going to be delta U for isothermal? Delta U is equal to 0 for isothermal change. Please do pay attention. This session is important. You will be able to attempt each and every question. Yes, everybody, is this clear, guys? Is this clear? Is this clear? So here, this is just a part of, this is just a, whatever I have explained about reversible and irreversible, right? This is just a gist of everything, okay? This is just basically a gist of everything. So are we clear with all of these things, bachos? Are we clear with all of these things? We are? We are? Yes? Yes, we are, right? Now can we do some gases? Sorry, not gases. Let's do some graphs, okay? Types of processes, let's do some graphs here. Okay, let's do some graphs. So, first of all, let's do isothermal. Isothermal, okay? Isothermal means delta T is equal to 0. Correct? Yes. Now, for all of these graphs, okay, we will be doing isothermal, isobaric, isochoric. For all of these graphs, the easiest way would be to PV is equal to nRT. Just take a look at, always have PV is equal to nRT, this formula near you, this formula fit in your head, and you will be able to do any graph that comes to you. Okay? Any graph that comes to you. So, sabse pehle, the first thing that we are going to do is, everybody, first thing that we are going to do is, let's take these two axes. Yes, these two axes, and let's say that I have V and T. This is V, this is T. Delta T is equal to 0. Delta T is equal to 0, right? Temperature is constant. If temperature is constant, then V is equal to nRT. V is equal to nRT divided by P. Then what can I do? This will be my graph, isn't it? This will be my graph, isn't it? Right? Am I right or wrong, everyone? Tell me. This is going to be my graph, correct? Correct? Okay, great. Next, everybody, let's do the same thing here. Let's do the same thing here. Now, let's say that I take P here and I take T here. Now, what will happen? Temperature is still constant, isn't it? Temperature is still constant. This time, what do I do? This time, what do I do? So, P is equal to nRT by V. T is constant, nR is anyway constant. Am I right? So, that means this is going to be my graph. Am I right? This is going to be my graph. Correct, everybody? Yes? Very good. Well done. Now, if I take this and this, okay, this and this, now I have P and V. Pressure versus V. Then my graph is going to be like this. Am I clear? Sorry, my hand shook a little bit. Sorry, my hand shook a little bit. Let's do this again. I think my hands are shaking now. Okay, let's do this again. This is going to be my graph. Am I right? Very good. Very good. Now we go to isobaric. Okay. Now we go to isobaric. For isobaric, delta P is equal to 0. Right? Delta P is equal to 0. So what will happen here is, again, same thing. Let's take P, pressure versus T. Then what will happen? This is the graph, isn't it? This is the graph. Correct, everybody? If I take pressure versus volume. If I take pressure versus volume, then again this is the graph, isn't it? Yes, this is going to be the graph. But if my graph from here to here, if it goes this side, then it will be expansion. And if it comes from point 2 to point 1, it will be contraction, right? And the last one, everybody, is volume versus temperature. How will the graph be? This time it will be somewhat like this. Clear? All right. Last one, everybody, isochoric. Isochoric. What will happen to isochoric? Isochoric also, let's take it, everybody. P, pressure versus volume. What will it be? This, right? If I have volume versus T, everybody, volume versus T, then what will happen? This will be my graph, isn't it? And if I have pressure, multiplied with T, then this will be my graph. Am I right, everybody? Yes. All right. Great. Okay. All right, everybody. Yes, then also there is cyclic graph. Cyclic graph, you all know, I have told you that cyclic graph is usually a loop, isn't it? Cyclic graph is usually a loop, correct? Yes. Now, everybody, can you all do this question? Can you all do this question? Let's try and solve it. What do you all think? Let's try and solve it, everybody. Shall we? Shall we? No. Yes? No. What should we do? What should we do, guys? Shall we solve it? Can you all solve it? Or no? Okay, read the question. Yes, graph is important. 10 mole of ideal gas expand isothermally and reversibly from a pressure of 10 atm to 1 atm, 10 atmospheric pressure to 1 atmospheric pressure at 300 Kelvin. What is the largest mass which can be lifted through a height of 100 meter? Any idea, everyone? How are we going to do it? Any idea? Yo. No? Yes? Mitesh, come on, yeah. We have done it so many times. Acha, anyway. What do we know? Work done is equal to 2.303. Yes. nRT, right? Log V1 divided by V2 we have done. So that means we can also write it as P1 divided by P2, isn't it? That, let's write it as equal to mgh, right? Yes. Now all the values are given to you. 2.303. What is n? N is given 10. 10. It's given. Yes, 10 is given. R is how much? R is equal to 8.3, right? Then you write what is T. T is also given to you. 300 Kelvin, isn't it? So 30 into 10 to the power 3 if I can write. That means I can also write it as M into 10 to the power 3, right? And now if you calculate M, how much will you get? Who is giving me? Jawbreaker is writing the answer that 58.5. Bro, I'm trusting you. Please tell me the correct answer. 58.55 kg. This is the answer, everybody. This is the answer. Please check it out. Please have a look and check it out. Is this the correct answer, everyone? Tell me. Ayo, work done in free expansion of gas. I've already done it. I've already done it. But chalo, it's okay. Correct? Chalo. Now everyone, work done in free expansion of gas that we have done. And I also told you that for isothermal change, delta U is equal to 0, if you remember, isn't it? For isothermal irreversible change, let's talk about for isothermal irreversible change, what will happen? For isothermal, I haven't told you about this, right? For isothermal irreversible change, now what will happen, everybody? For isothermal irreversible change, Q will be equal to minus W is equal to P external, yes, V final minus V initial. Yes, this is the answer, okay? This is going to be the relation. But for isothermal reversible change, everybody, for isothermal reversible change, what will happen, everyone? For isothermal reversible change, let's have a look at it. Yes, let's have a look at it. I will, Tanay, I will. Don't worry about it. Okay. For isothermal reversible change, everybody, my Q will be equal to minus W, right? Minus W is equal to nRT. 1 second. Let me not write it here because I will not be able to complete it here. So let's go this side. Yes, it will be what? nRT. T. Yes, ln Vf divided by V1. Yes, right? This is exactly what we have spoken some time back only. Now, because I have written ln here, then what I can do next? Next, I have to write it 2.303 nRT. Oh, my brain and hand coordination is lost now. nRT log Vf divided by Vi, isn't it? Yes. And for adiabatic change, Q is equal to 0. Let's write that also. Okay? For adiabatic change, what will happen? Q is equal to 0. Yes, Q is equal to 0. Then delta U is equal to WAD. Why AD? Adiabatic change, right? Adiabatic change. That is why. First law of thermodynamics, I guess it's already done. Mathematical form of first law of thermodynamics is also done. Yes, anything else is left? Sign convention of work and heat. Yes, this is important, guys. This is important. Sign convention. Please understand this, okay? So if the work done is on the system, then what will happen? It will be positive, right? If the work done is by the system, then it is going to be negative. Isn't it, everybody? Please check it out. If the work done is on the system, then what happens? It will be positive. Why? Because the system is getting more of substances, isn't it? So this is going to be positive. But if the work done is by the system, if the system does the work, then what is happening? Some amount of it is leaving. Then the work done becomes negative. What is it in? As in? This is the sign convention of work and heat in first law of thermodynamics. Okay? Alright. Then if Q is what? Heat is absorbed by the system from the surrounding, then it is going to be positive. And if the heat is released by the system, then it is going to be negative. Is this clear, everybody? Yes. Acha. Now, tell me something. Which of the following is a state function and it is also an extensive property? Can you guys tell me? Which of the following is a state function and also an extensive property, everybody? Which one? State function depends on the state, depends on just the change. What is it? All this time we were talking about this only, everybody, right? Isn't it internal energy, my dear students? Internal energy, delta U, delta E. Yes, delta U, we kept talking about it. Delta U, delta E, delta U, delta E. So state function, it is a state function and it is also an extensive property. Am I clear, everybody? Yes. Now we will read about enthalpy. Everybody ready? Yes, everybody ready? After some time, we will also have to talk about. Then we will also be talking about. Acha, have I taught you specific heat capacity and heat capacity? Have I taught you about specific heat capacity and heat capacity? If not, then it is important that I teach you right now. Have I taught you about specific heat capacity and heat capacity? Yes, guys. Yes or no? Please tell me. Actually, let me see if it is there sometime. Acha, no, heat capacity is after enthalpy. After enthalpy, we have to learn about specific heat capacity. Oh, thank God the headings are there. Otherwise, I would have already forgotten that what it is. Anyway, acha. No, right? No worries, no worries. We will do it after enthalpy. After enthalpy, heat capacity and specific heat capacity is there. Then we have to learn about some of the, relations and formula from there. No worries, no worries. It's okay, it's okay. After enthalpy. We'll do it after enthalpy. Okay? Yes. So enthalpy, everybody, is a state function, isn't it? Enthalpy is a state function and I think we have read about this already. So we know about it, right? And most of the chemical reaction here, what happens is it takes place in open air. That means at constant pressure. Okay. That means at constant pressure. What did I say, everybody? I said that most of the chemical reaction, okay, most of the chemical reaction, understand this, what is happening here? Most of the chemical reaction takes place in open air, that is at constant pressure. That is at constant pressure, right? So that means everybody, let's have a look at the derivation, okay? Because we have been talking about this, isn't it? So let's see that delta U is equal to Q plus W, right? Q plus W. What is my W, everybody? My W is minus P delta V, isn't it? Minus P delta V, isn't it, everybody? And since it is constant pressure, everyone, will you all agree if I write this as QP? If I write this as QP, can I say that? Can I say that, everybody? Yes, let's derive, okay? All right, yes. So that means that delta U is equal to, everybody, delta U is equal to what? U2 minus U1, right? Now, this can be equal to QP minus P, and what is this delta V, everybody? What is this delta V, guys? The delta V, everyone, right here is, what is my delta V here? Delta V is going to be V2 minus V1. Can I write that? Can I write that? Yes, very good, I can. Now that means that what is my QP? My QP becomes, everybody, check it out, U2 minus U1 plus PV2 minus PV1. Can I write that? Can I write that? Yes, very good. So that means QP becomes, everyone, QP becomes, let's just reshuffle this. So U2 plus PV2, and I can minus U1 plus PV1. Make sense? Make sense, everybody? And somebody had already written that, yes, Kamal has written that H is equal to U plus PV. H is equal to U plus PV. This is something that we know, right? This is something that we know. So that means here, that from this equation, everybody, can I not write it as QP is equal to H2 minus H1, and what is my H? H is equal to U plus PV. That means that QP is equal to delta H. Am I right? And what is my delta H, bachchus? Delta H is equal to delta U plus P delta V. This is super important. Yes, this is super important. Sannyasi, have you come to the session only for my response, or have you come to the session to learn something? If you have come here to learn, then bacha, learn, no? You ask me a doubt, I will answer. Please, shh. Already 2 hours, more than 2 hours of the session has gone. Suddenly you come here, you say hi, and then please respond to my message. Please respond to my message. Why are you breaking the flow of the session? Don't do that. Yeah? You have come here to study? Study. Shh. Okay. Now let's understand, everybody. Now, can I say that when will be my delta H negative? When will be my delta H negative? Delta H will be negative when there is an exothermic reaction. That means that the reaction will evolve heat. When the reaction will evolve heat, that time my delta H is going to be negative. So let's write it down. Delta H is negative when? For exothermic reaction. For exothermic reaction. Yes, right? And you know what is exothermic reaction, right? What is exothermic reaction? Evolves heat. Evolves heat. Correct? Yes. Now, when is delta H going to be positive? Delta H is positive. Delta H is positive for endothermic reaction. Yes. What is endothermic reaction? Endothermic reaction is basically absorbs heat, right? Absorbs heat. Clear? Yes, everybody? Yes? Very good, very good, very good. What is enthalpy? Enthalpy, all these things that I have done it here, enthalpy is internal energy plus pressure and volume, okay? Pressure multiplied with volume plus your internal energy, that is your enthalpy, okay? Crystal clear, everybody? Yes. Now let's understand that delta H and delta U. Yes. So very good, very good. Janvi, you have actually asked me this at the very right time. Okay. All right. And anyway, all of these are written here. So please check it out. Whatever I have taught you, everything is right here, everyone. When a process takes place at a constant pressure, when a process takes place at constant pressure, that means that any and every reaction that is happening right now, your vegetables getting rotten, enthalpy. Yes, because why? We are always under one single pressure, isn't it? We only have the atmospheric pressure that is acting on our head, right? So when a process takes place at constant pressure, the heat absorbed or released is equal to the enthalpy change. Okay, that is equal to enthalpy change. Yes, everybody understanding the change in enthalpy is measured when the heat is added or lost. What is enthalpy? Enthalpy is the sum of the system's internal energy and the product of pressure and volume. Janvi understood? Janvi understood, everyone? Yes, guys? Yes? Acha, now I need a little more. I do need some extra pages. This is same, right? Just a second, guys. Just a second. I need some extra more pages to be able to explain you the difference between internal energy and enthalpy change. You might get confused, right? Like Janvi is asking right now. So let me explain this as well to you. Okay. All right. Yes. So what is delta U and delta H? Delta U was what? Internal energy, right? And what is delta H? Delta H is the enthalpy change, right? So the difference between enthalpy change and the internal energy, sometimes it is not very, it's not very, how do you say, like, it's not very significant. It's not very significant. You know why? Only for solids and liquids is not very significant. For gas, it is definitely significant, bacha. For gas, it is definitely significant, but for solids and liquids, it's not very significant. Why? Because in case of solids and liquid, remember, we have studied that solids and liquids are rigid. They are not compressible. That means that delta V is almost the there is no significant change in delta V. If there is no significant change in delta V, then my P delta V is equal to 0 because delta V is what? Change in the volume. There is no significant change in volume. Delta V is 0. If delta V is 0, then P delta V is also 0. And then what happens? Only so during when we are talking about a solid or a liquid, then delta H becomes equal to delta U. True. But what about enthalpy of gases? So we mostly consider enthalpy of gases. Absolutely. Yes, and now you will understand, everybody. So let's talk about this. Yes, what was I saying? I was saying delta H and delta U. What is the difference between internal energy and your enthalpy change, right? So what did I say, everybody? Let's just write it down. Just write it down, everyone. Yes, so that every notes is right in front of you. Okay. The difference between delta H and delta U is not very significant. Okay, is not very significant for systems consisting of only solids or liquids. Yes, All right. Why? Why? Because I have just explained that, if there is not, write it down, if there is not any significant change, bachos, if there is not any significant change in delta V, then what will happen? Then P delta V is equal to 0 and delta H becomes equal to delta U. Make sense? Yes? Make sense, everybody? Yes? Great. Okay. All right. Yes. So the difference between delta H and delta U, okay? What is the difference between delta H and delta U, or when does it become significant? It becomes significant only when gases are involved, okay? Yes? Delta H and delta U difference becomes significant only when gases are involved. Clear, everybody? Yes. So now that I have told you that only during gases the delta H and delta U difference becomes significant. So what are we going to do? Now we have to understand enthalpy of gases, isn't it? Now we will have to understand enthalpy of gases. So shall we, everybody? So chalo, let's talk about that. Yes, let's talk about that. Is that so? 562.7 kg आ रहा है. Is that so? Which one was it? Here. Same only, no? 572 point, how much? 62.7. Acha guys, you please check it out, no? Please check it out. There is also a possibility of the answer that it is 562.7 kg. Please check it out, everybody, okay? Please check it out. I don't know the answer. I don't know the answer. Okay? Please check it out. Bachchu, who is that asking me this question? Huh? Who is that asking me this question? Can we mention enthalpy without change in enthalpy? Bachchu, enthalpy is a state function. When it is state function, this delta U, delta H, delta G, these all are state function. You can only measure the difference. You can measure the difference. You can't measure the absolute thing. Okay? Alright, we have spoken about this in the very beginning of the session, Bachchu. You should have been there, right? You were not there in the very beginning, that means. Chalo, anyway, yes. So now let's talk about enthalpy of gases, shall we? Yes, enthalpy of gases we are going to talk about. Acha. So in case of a gas, what will happen? In case of a gas, let's say that we take two gases. Okay, let's say that we take two gases. We have gas A and gas B. Okay, let's say that we have taken, it was 100% correct answer. Then chalo, somebody will check it out. Anyway, it will stay in the video. Somebody else will check it out. Whoever it is, please check it out. I'm not calculating. I've told you how to calculate. After that, the calculation part, you can do it. Now, you have the calculator. You are supposed to be more clear about calculation, not me. My days are gone. I don't have to calculate. I don't require maths. Only time I require maths is, Bhaiya, aloo dena. How much? Aloo is 5 kg. 5 kg. How much is 1 kg? 1 kg aloo is, let's say, 30 rupees. So I have to only calculate that 5 into 30 is 150 rupees I have to give. So that's all I calculate, nothing else. You are in grade 11. Can I get 99%? Oh, absolutely. You have a lot of time. Start studying from right now. Just don't waste your class 11th. Okay. All right. So everybody, let's say that we have two gases. Okay. Volume of gas A. Total volume of gas reactant. Oh, did I say two gases? No. One gas. Sorry. One gas. Everybody, one gas. Pay attention, everyone. One gas. Okay. It's one gas, everybody. So, total volume of gas in the reactant side. Okay. Total volume of the gas in the reactant side. Okay. Yes. Then, total volume of gas in the product side. Okay. All right. Yes. Okay. Then what do we have? We will also have Na. What is Na? Moles of total moles of gas reactants. All right. And what is Nb? Total moles of gas products. Total moles of gas products. So if I have written Va, Vb, Na, Nb, then what do you understand? That means that I am coming to the equation that is called as what? Ideal gas. Correcto? Yes. And if I am talking about ideal gas, bacha, you also have to understand, what did I tell you? Enthalpy. Everything is happening at constant pressure. Yes. Very good. Constant pressure. This is all happening at constant pressure. This is what we just spoke about, right? Enthalpy. Enthalpy is happening at constant pressure. Remember it. So, ideal gas equation is basically PVA is equal to NART for the reactant side. And for the product side, it becomes PVB is equal to NBRT. Make it sense? Great. Now, what do I have? Let's consider P to be same, right? If I take P here, P common. Let's take P to be common, right? Now what will I have? I will have VB minus VA, right? Great. Then this side what will I have? This side I will have NB minus NA. RT can be taken common, obviously. RT can be taken common, correct? RT can be taken common, am I right? Yes. So now where are we getting it? Where are we getting it, everybody? What is happening? What is happening, guys? Tell me. Yo. Now what is going to happen? Wait, yeah, I have forgotten after this what I had to teach you. Just a second, let me consult my notes a little bit. I have been teaching for a very long time and my mind is not working anymore. So, where is my notes? I have to check my notes. Whew. Oh, nothing. After this, all we have to do is, acha. Huh. So, VB minus VA, bacha. All are sleeping. Nah, yeah, no, please don't sleep, guys. You are, yes. Very good, everybody. Okay. Yes, so what we can do is VB minus VA, right? So that means P delta V, right? P delta V is equal to delta nRT because NB minus NA, right? And that means if what is P delta V? P delta V, everybody, is equal to delta H minus delta U, if you remember. Yes, and that is equal to delta nRT. Am I right? Very good. Very good. Yes. Now this equation I can just slightly tweak it. Okay. I can tweak it and see what I will get. Okay. See what I will get. I will get it as delta H is equal to delta U plus delta N in suffix. What do you call it? Subscript. Yes. In subscript, you can write Ng because this is for gases, isn't it? NGRT. And this is another of your important this is another of your important this thing. Okay. All right. Yes. Now we will come to specific heat capacity. Yes. Now we will come to specific heat capacity, isn't it? After that specific heat capacity, then we have to do Cp and Cv, constant pressure and constant volume in an ideal gas. Okay. All right. Yes. Enthalpy is done, everybody. Sorry. Enthalpy is done. Okay, great. Yeah. This is what we have to do. Chalo, heat capacity. Guys, what is heat capacity, everybody? I haven't done heat capacity, right? What is heat capacity? Heat capacity bole to amount of heat that is required or absorbed by a system, okay? For example, if I have a system right here, if this is my system, the amount of heat that is required by this system or it is absorbed by the system to raise the temperature raise the temperature by 1 degree of a given mass. What did I say? Raise the temperature by 1 degree of a given mass. All right, everybody? Yes. So let's write it down. Let's write it down. What is heat capacity? Heat capacity is basically amount of heat required. Okay. Amount of heat required, or we can say that, or amount of heat absorbed, right? Or absorbed by a system to raise the temperature of a given mass by unit degree. By unit degree, isn't it? So how do you denote heat capacity? You denote it as C subscript T. How do you denote it? C subscript T. And what is our formula? Mathematically, you can write it as CT delta T, isn't it? Or you can write it as CT is equal to Q divided by delta T. Am I right, everybody? Yes? Yes, very good. Yes, correct. Great. Okay. Now we have something called as specific. The moment you see specific, you remember even in your junior grades, you have studied about specific. Specific means that the moment you see specific, you have to understand that the amount of heat required to raise the temperature of unit mass. Very good. Unit mass by 1 degree Celsius. Yes, unit mass by 1 degree Celsius. Very good. So what do we write here? We write that quantity or amount of heat. Let's write, right? Same we will write. Yes. Amount of heat required to raise the temperature of unit mass. Unit mass, then what did I say? Unit mass of a substance. Yes, unit mass of a substance by 1 degree Celsius. Yes, by 1 degree Celsius. And what is this time going to be what is going to be the mathematical relation? Q is equal to MC delta T. Yes, MC is your specific heat capacity. All right. Yes, everybody. Now, let's write a relation between. Okay, let's talk about a relationship between here. These are all important formula. Chalo, here let's do it. Okay, here let's do it, everybody. What is it? Relation between constant pressure and constant volume. Okay, relation between Cp and Cv. Okay, Cv in an ideal gas. What is the specific heat of mercury? How do I know? Do you think I'm a Wikipedia? No, you can search that on internet. Find it out. Cp and Cv in an ideal gas. Okay, in an ideal gas. But that's not a doubt here. That's you thinking that I'm a Wikipedia. I'm not. That's not a doubt. Okay, these kind of question that what is the this thing, what is the that thing, all that you can find on this thing. You ask me about concepts that I will clarify for you. Okay, so at constant volume, everyone, at constant volume, what do you know? We know that QV is equal to delta U. Correct? Right, everybody? Great. Now, at constant pressure, what do we know? We know that QP is equal to delta H. Correct? Very good. So now delta H is equal to delta U plus P delta V. This is something that we already know, right? If that is the case, then can I also not write it as QP is equal to QV plus P delta V? Can I not write it like this? Yes. P delta V. Can I not write it like this? I can, right? Now, what if I'm taking 1 mole of ideal gas? For 1 mole of ideal gas, bachus, check it out. For 1 mole of ideal gas, what am I going to do? For 1 mole of ideal gas, everybody, please check it out. What will I get? I will get P delta V is equal to R delta T, isn't it? Yes. And that means, everybody, that QP is equal to QV plus R delta T. Am I right? Yes. Now, can we utilize the heat concept, the heat capacity concept that we have just spoken about? Yes. Can we utilize the heat capacity concept? We can. And what will we see? We will see that Q is equal to C delta T. Yes. And we also know that QP is equal to CP delta T. Correct? Yes. And that means, everybody, please check it out, check it out, check it out. Everybody have a look. CP delta T is equal to CV delta T plus R delta T. Am I right? Am I right? Yes, I am. Now what I can do is CP delta T is equal to CV plus R, and delta T can be taken common, right? And if that is the case, everybody, from here directly I can see that CP minus CV is equal to R, because delta T and delta T can get cancelled, right? Delta T and delta T can get cancelled, so I can directly write it as CP minus CV is equal to R. So this is the relation that is once again important for you, okay? This relation is once again important for you, everybody, okay? All right. Now that we are done with the heat capacity and we are done with specific heat capacity, you have to understand that there are some important formula that we have to study, okay? So, let's get done with them one by one, everybody. Number one, everybody. What is number one? Number one is molar heat capacity, CM. What is CM? CM is equal to plus Q divided by N delta T, okay? Plus Q divided by N delta T, all right? Yes. Will you teach graphs? I have already taught you graphs. I've already taught you graphs, bacha. Yes. Whatever, all the important graphs of isochoric, isobaric, yes, isothermal, I've already taught you. Please watch it from the very beginning, okay? Then what do we have? Next we have is specific heat capacity that I've just taught you. What is specific heat capacity? It is plus Q divided by W delta T, isn't it? Yes. Now what do we have? We have CP. CP is also something that we have just learned. This will be plus QP divided by delta T. All right. Yes, great. Okay. Now what do we have? We have CPM. What is CPM? Molar heat capacity at constant pressure, isn't it? Molar heat capacity at constant pressure. So this will be plus QP divided by N delta T. Am I right? Very good. Okay. Next here. Fifth formula, everybody. What is fifth formula? We are done with molar heat capacity. So CPS. What is CPS? Specific heat capacity. This is plus QP divided by W delta T. Am I right, everyone? Very good. Next, we have CV. What is CV? Heat capacity at constant volume. So, CV is equal to plus QV divided by delta T. Makes sense, everybody? Great. Okay. Then what do we have? We have CVM. CVM is obviously same as molar heat capacity at constant volume. So, plus QV divided by delta T, obviously, but what will come here? N. Very good. N is what? Mole. Very good. Yes. Then what do we have here? 1, 2, this is 8. Eighth one is CVS. What is it? Specific heat at constant volume. So this will be plus QV divided by W delta T. Clear? Yes? Great. Very good. Acha, now here are also some... Okay, need another page, guys. Okay. Here, this is not enthalpy, okay? This is not enthalpy. Please understand, this is not enthalpy. What are we doing? Here, there are some important relations, okay? There are some important relations. What are the important relations? Please understand that isothermal, okay? For isothermal, everybody, for isothermal, you will see that C is equal to infinite, okay? All right. For isobaric, For an isobaric process, C is equal to Cp. Alright. For isochoric, you will see that C is equal to Cv. Alright. And for adiabatic, everybody, for adiabatic, what will happen? For adiabatic, you will know that Q is equal to 0. So C is equal to 0. Am I right, everyone? Yes? Yes? Very good. Ha, Deepti, you know it. Very good, bacha. Very good. Yes. Now what is happening is, then there is something called as Myers relation. Okay. Myers relation. Yes. Or Mayer's relation. Mayer's relation, I think. Not Meyer. Mayer's relation. Yes. Bhola, bro, why aren't you paying attention? These are the things that I've taught you. What is heat required to increase the temperature by 1 degree of water? You tell me. I've taught you this, na? Heat capacity, specific heat capacity. You tell me, bacha. Yes? You tell me. I've taught you the concept. Please tell me. What is it? Chalo. Now, this is called as Mayer's relation. What is Mayer's relation? We have just done it. We have just done it. We have just done it, everybody. We have just done it. Yes. But any which way, let me tell you here that CPM minus CVM is equal to R. This is your Mayer's relation. Okay. This is your Mayer's relation. We have just some time back only we have done it. Okay. Now, heat capacity. Heat capacity is a path function. All right. Heat capacity at a constant temperature, that is CT, it is a path function. But CP and CV, they are not path function. Rather, no. Sorry, what did I say? Yes, I just told you that heat capacity is a path function, whereas CP and CV, they are constants and they are not path function. Okay. CP and CV, they are constant and they are not path function. All right, everybody. Is this clear? Is this clear? Okay. All right. So we are done with these things. We're done with these things. Then what is left? Cp by Cv is equal to R. Acha. Degree of freedom. Degree of freedom we have to do. Chalo. Here also you will have a table. Okay. Here also you will have a table. Correct? Yeah. So, this is gamma. Gamma is equal to Cp divided by Cv. All right. And another formula for gamma is 1 plus 2 divided by F. What is F? F is your degree of freedom. Okay. F is your degree of freedom. You're going to ask me that, ma'am, what is this degree of freedom, everybody? What is this degree of freedom? What do you think? Degree of freedom is basically the mode of movement, right? For example, when your teacher is not there in the class, what happens? When your teacher is not there in the class, what happens? All of you are like, "Wah!" The degree of freedom is much more, isn't it? Yes. The degree of freedom is much more, right? Yes. But the moment your teacher is inside, then what happens? The moment the teacher is inside, you're all like, shh, quiet. Correct? Correct, everybody? Yes. So then there are monoatomic gases, there are diatomic gases, there are triatomic gases, right? So let's talk about that. Yes, let's talk about that. We have monoatomic gas, we have monoatomic gas, right? We have diatomic gas, right? And we have triatomic gas, okay? And we have triatomic gas, but please note it down that this is non-linear, okay? What is this? This is non-linear. So first of all, we have here F, okay? Then what do we have here? We have here Cp minus Cv is equal to R. Then we have here, everybody, okay, this is a table. Please make it note of it, okay? Then what do we have? We have Cv is equal to F multiplied with R divided by 2, and finally you find the gamma, okay? All right. These are the 4 columns that we have. So, chalo. First of all, for a monoatomic gas, let's just say that this is one atom. This is one atom. So, how will this move? This will move in its axis like this. Imagine that this is your y-axis, right? This is your y-axis. This is your x-axis, yes. And this can be your z-axis, right? So, there are 3 ways that it can move, isn't it? There are 3 ways that it is moving. Great, okay. So, let's write here 3t plus. Rotation. Rotation is probably happening, but maybe in its own axis rotation is happening, isn't it? Maybe it is happening in its own axis. So can we consider? No, we do not consider. So this will be 0r. So that means this F is equal to degree of freedom is only 3. Okay. Now what we will do is F multiplied with R by 2. So that means this will become everybody, this will become 3R by 2. Yes. Now 3R by 2, and this is CV. So CV plus R. What will this become? This will become 5R by 2. Correct? Yes. And then if I remove the R, that will become my ratio. So 5 by 3, isn't it? That will become my ratio 5 by 3. Correct. Very good. Yes. Now we have diatomic. Yes, but diatomic is also very similar. Basically, let's now consider that I have here. No. For diatomic, everybody. Oh yeah, I have. Okay. Consider this to be our diatomic gas, right? How will this move? This is, and imagine this is bonded, okay? Imagine that this is bonded, right? How will it move? Same like this, XX, YY, and it will move like this also, ZZ, right? Now, how else it can move? It can move like this. It can rotate like this. It can also rotate like this, right? It can also rotate like this, and it can move in its axis also, but that we will not consider, isn't it? That we will not consider. So that means that 3T plus 2R, isn't it? Which is equal to 5, everybody. Yes. So that means if I have to write for CV, then what will I get? I will get 5R divided by 2, plus R. It will become 7R divided by 2. Am I right? That means that this will become 7 divided by 5. Am I right? Very good. Yes. Now if I have triatomic. Acha. For triatomic, basically we have something like this, right? Triatomic will be basically like this, isn't it? Yes, if it is like this, now imagine, same like this, x-axis, z-axis, and then y-axis, right? Yes. Apart from that, it can rotate like this, right? It can also rotate like this, correct? Yes. Then how else can it move? It can also rotate like this, right? It can also rotate like this. Yes. So there are 3 rotational motion and 3 translatory motions. So 3T plus 3R is equal to 6. So that means here we will get 6R by 2. 6R by 2 is basically equal to 3R. So 3R plus 1R is equal to 4R. That means this will be 4 divided by 3. Clear, everybody? Is this clear? Yes. Is this clear? Okay. So all of these are done. See, this is your Poisson's ratio. This gamma is equal to Cp divided by Cv. That is your Poisson's ratio, and that is what I have written here. Okay. This is your gamma. See, gamma is equal to Poisson's ratio. I have done it here. Right? And gamma is equal to 1 plus 2 by F. All of that is done. Okay. Clear? Everybody? Yes. Adiabatic process and Poisson's ratio. I don't think I have to write anything here. Oh, that is what I had to write. Chalo. Yes. Chalo, done. Acha, let's skip the problems now, okay? Let's skip the problems now and let's quickly finish the session. What do you all say? Let's quickly finish the session. Let's do reaction enthalpy. Problems, I'll take it tomorrow, okay? Problems, I'll take it tomorrow. Advanced to basic, everything, I will do it tomorrow. Chalo. The enthalpy change accompanying a reaction is called the reaction enthalpy. Okay, what is reaction enthalpy? Basically, when there is a reaction that is happening and with that, if there is an enthalpy change, then that is what is called as a reaction enthalpy. So let's write it down, everybody. What did I say? The enthalpy change, okay? The enthalpy change accompanying, okay? The enthalpy change accompanying a reaction is called the reaction enthalpy. All right. Yes. Now what is it? It is the heat content of the system. It also decides if the reaction will happen or not. Okay. It also decides if the reaction will happen or not. So what can I say? I can also write it that it decides whether the reaction will happen or not. Cool? Yes. All right. It is also the heat content of the system. It is the heat content of the system. Cool. All right. Yes. So now what is happening in a reaction? In a reaction, usually we see that there are some reactants and the reactants, they get converted to products, right? Yes, we always know this. There are reactants, the reactants, they get converted to products, correct? Yes. Now, what am I saying? Does it make sense? Tell me, okay? Does it make sense to you? Tell me. So, I have reactants here. I have reactants here and the reactants, they get converted to your products, correct? Yes, everybody. So, now what will happen is, because I'm talking about reaction enthalpy, okay? Reaction enthalpy that I'm talking about, that means, you know, in this chapter, everywhere you will see delta H, delta G, delta S, delta H, delta U, delta E, all of these, right? And everywhere you will see a subscript or a superscript. So right here, tell me what is going to be the subscript here, because it is reaction enthalpy, we will write delta R. Simple and easy, right? Simple and easy. Understandable. So we are going to write delta RH. Basically, what is it going to be? What is this reaction enthalpy going to be? The reaction enthalpy is going to be basically the sum of enthalpies of products. The sum of enthalpies of products, yes, minus sum of enthalpies of reactants. Make sense? E. Yes, makes sense? Very good, very good. How do I write it? No integration, summation, remember? Yes, no integration, summation. What do I write? I here, summation of AIH products. This is exactly there in your NCERT, everybody. If you have just opened it and if you have seen, you would have noticed that there is AIBI. Yes, AIBIH reactant, isn't it there? Yes. What is AI and BI? AI and BI are stoichiometric coefficients. What are AI and BI? AI and BI are stoichiometric coefficient. What is AI and BI? These are stoichiometric coefficients. All right. Yes. Of the balanced reaction. Yes. By the way, this has to be balanced. Okay. Of the balanced reaction. This has to be balanced. Okay. Of the balanced reaction, guys. Great. Okay. So, for example, if I have a reaction like this, AA plus BB gives you CC plus D, capital D. Right. How am I going to write the delta R? How am I going to write the reaction enthalpy? My reaction enthalpy will be delta RH is equal to small c capital H of capital C plus small d capital H of capital D, right? Because this is the product side, right? Now the reactant side, what will be the reactant side? Small a capital H of capital A plus small b capital H of capital B. Clear hai everybody? Yes? Clear hai? Yes? Alright guys. Okay. Now from here we come to something called as standard enthalpy of reaction. Obviously, reaction enthalpy is done. So now we will do standard enthalpy of reaction. Okay. What is standard enthalpy of reaction? Standard reaction enthalpy or standard enthalpy of reaction. This is denoted as delta H and then there is a circle with a mark. Like this is called as theta. Okay. This is called as theta. Spontaneity is coming. Wait for some time. First, let's do a reaction enthalpy. Okay. So what is this? What is standard? Like I said, there has to be unit, right? There has to be something that is unit. So what will this be? This will be enthalpy change. Enthalpy change for a reaction. Enthalpy change for a reaction when all the participating substances are in their standard states. Everybody has to be in their standard state, okay? And where is it performed? When is it performed? It is performed at not performed, basically they are all standard states, standards. What is going on? Sorry, I think I'm sleepy now. Anyway, when we say standard states means, you know, we have studied about this in redox reaction. That means pure form, it has to be in 298 Kelvin and at 1 bar atmospheric pressure, right? So 1 bar atmospheric pressure, 298 Kelvin, and it has to be in its pure form, right? Yes, in its pure form. Got it? All right. Now where we come to is we come across something called as, okay, now we come across something called as delta H. What is delta H? Delta H is enthalpy change, right? Delta H during phase transformations, okay? Delta H during phase transformations. This is no longer reaction enthalpy. This is, oh, we have to read a lot, guys. We have to read a lot. There is a lot of, this thing is remaining, everybody. We will be doing now delta H during phase transformation. Now, there are obviously different phase transformations, right? There are obviously different types of phase transformation. What is phase? Solid to liquid, liquid to gas, gas to solid, or solid to directly gas, isn't it? Yes, these are the ones that are there. Yes, so that means that we have 3 different phase transformation. What is it? Standard enthalpy of fusion, standard enthalpy of fusion. Okay, all right. Then what do we have? We have standard enthalpy of vaporization. All right. And finally, what do we have? We have standard enthalpy of sublimation. Am I right, everybody? Great. Yes. Okay. Okay, so now let's learn about these things. Yes, now let's learn about these things, everybody. So what do we have? First, we have standard enthalpy of fusion, right? What do we have? We have standard enthalpy of fusion. So what is standard enthalpy of fusion and how is it denoted? Standard enthalpy of fusion is basically enthalpy change that accompanies melting of 1 mole of a solid substance in a standard state. Standard state, right, everybody? Yes. Can you take only 2 minutes break? I don't think so. Let's finish it. I want to sleep by 11:30. So let's give it another 1 hour or so. Yeah, by 11:30, let's finish it, bachos, because I have to sleep. So let's quickly get done with this. Okay, let's quickly get done with this. Chalo. I don't want to delay it anymore. So let's quickly get done with this and then we will finish. We will sleep. Okay. I also have to, no worries. You can go and eat and come back. Okay. You can go and eat and come back, okay? Because see, I also have to get up early in the morning. I have to get up at 5 o'clock because, you know, ma'am goes to the gym and I learn mixed martial arts and everything. So I have to go at 5 a.m. in the morning. I have to get up 5:30. I have to reach the gym. So everybody, let's quickly finish it. Come on. Okay. All right. Enthalpy change, okay? What is it? Enthalpy change that accompanies Yeah, I had dinner at 6:30. I had dinner at 6:30. Praveen, bacha, spontaneity will come. Spontaneity will come. Chill mari. For spontaneity to come, you have to go through standard enthalpy of fusion, vaporization, then you will come across, you know, thermochemical equation, then you will come across Hess's law of constant heat summation, Then you will come across standard enthalpy types, enthalpy of combustion, and all of that. Yeah, I had dinner already. Yes, I already had dinner. Yes. Then we will talk a little bit about polyatomic, this thing, lattice enthalpy, Born-Haber cycle. Yes. Dilution versus solution, enthalpy of solution, enthalpy of dilution. We will talk about. Then will come spontaneity. So chill. It will come, but you will have to give it some time. Okay. It will come. Don't worry. Okay. So standard enthalpy of fusion, everybody. Enthalpy change that accompanies melting of aha. Acha, chalo, I'm going to dictate it. My battery has gone. Yes. What is it? Please write it down. Enthalpy change that accompanies melting of 1 mole of a solid. Okay. Melting of 1 mole of a solid. Okay. 1 mole of a solid substance. 1 mole of a solid substance in a standard state. Okay. In a standard state. Right. These are all there in your NCERT, everybody. Okay. These are all there in your NCERT. Okay. Yes. Okay. All right. So that means that delta H naught, but here I will have to write fusion, right? This will be equal to endothermic reaction. What will this be? This will be endothermic reaction. Am I right, everybody? This will be endothermic reaction. Okay. Yes. Yeah. Hey, Aman. Shh. Now don't talk too much. This is going a little beyond our classes. Okay. Then we write about standard enthalpy of vaporization. Okay, standard enthalpy of vaporization. What is standard enthalpy of vaporization? Same thing, you have to write amount of heat required to vaporize 1 mole of a liquid at standard state. Can you all write that down, everybody? Yes, can you all write that down or no? Amount of heat required to vaporize, okay, required to vaporize 1 mole of a liquid at standard states. At standard state. That means same delta H, this theta sign. But here what will you write? You will write VAP. That is vaporization. This is also going to be an endothermic reaction. This is also going to be endothermic reaction. Okay. All right, everybody. Is this clear? Is this clear? Great. Now what do we write? We write standard enthalpy of sublimation. What is standard enthalpy of sublimation, everybody? This is change in enthalpy when 1 mole of a solid substance sublimes. Okay. All right. Same thing. Can you all write it now? Can you all write it now? Or should I still write it, everybody? I think we can save some time here if you can write it. But chalo, theek hai. Change in enthalpy. Yes. Yes. Change in enthalpy when 1 mole of a substance, when 1 mole of a solid substance sublimes at a standard state. Okay. All right. Same thing, everybody. Delta sub H here this. This is also going to be an endothermic reaction. This is also going to be an endothermic reaction. Okay. All right, everybody. Yes. Now, who will tell you that how much of enthalpy has happened? Who is going to tell you that enthalpy change? Yes, there is an enthalpy change with the reaction. We understand. But what is the magnitude? Who is going to give us the strength of the enthalpy change? It depends on the intermolecular reaction. Okay. It depends on intermolecular reaction. Anyway, now there is also something called a standard enthalpy of formation. What is standard enthalpy of formation? Standard enthalpy of formation basically means standard enthalpy change for the formation of 1 mole of a compound from its elements in their reference state. Okay, all right, elements in their reference state. For example, you all know that Na plus is in solid, but Cl in its elemental state is what? Gaseous, right? It is in gaseous state. So from Na solid and Cl gaseous, when it forms NaCl, and that to 1 mole, that to also 1 mole, that time it is called as what? That time it is called as standard enthalpy of formation. Okay, all right, it is called as standard enthalpy of formation or standard molar enthalpy of formation. All right, yes, understanding everybody? Is this clear? Now you also have to understand that standard molar enthalpy of formation is actually just a special case of reaction enthalpy. But what do you mean by this? What do you mean by this? Again, this is there in your NCERT. If you just go and read about it a little bit, I think you will understand that the components, in case of standard molar enthalpy, what happens is that the components, they should always form from its constituent elements and not other compounds. But in case of reaction enthalpy, yes, in case of reaction enthalpy, we know that they can form from the elemental, they can form from the constituent elements or other compounds also. Yes. In the standard molar enthalpy of formation, it should always be 1 mole of compound that should be formed. But in this case, this is not necessary. Okay, it is not necessary. Am I clear, everybody? Now we come to something called as thermochemical equation. Okay, all right. Yes, now we come to thermochemical equation. What is a thermochemical equation? Bacha, thermochemical equation is a balanced chemical reaction with its value, with its reaction enthalpy value. Okay, all right. Yes, what is it? A balanced chemical equation, a balanced chemical equation together with the value of its, okay, all right. Bacha, go and eat. No worries. You can come back and join. That 2 minutes that you lose, you can watch it later. Please go. It's fine. Okay. All right. Now, in a thermochemical equation, what happens is the numerical value of delta H, it refers to the number of moles of substance. Normally in a chemical equation, everybody, yes, and normally in a chemical equation, we always say that when I say 3O2, right? When I say 3O2, what does it mean? We usually mean that it means 3 molecules, but in this scenario, it will not mean molecules. It will mean moles. What will it mean? It will mean moles, everybody. So please write it down. Please write it down, everybody, that numerical value of delta H refers to the number of moles of substances. Okay, all right. Yes, everybody, great. Next, what is it? The coefficient in a balanced thermochemical equation, they always refer to the number of moles, not molecules. Okay, coefficient, everybody write it down. Coefficients in a balanced thermochemical equation. Okay, balanced thermochemical equation will refer to, okay, will refer to what? To the number of mole. Equation refers to the number of moles and not molecules. Please pay attention here, okay? And not molecules. Please pay attention, everybody. This is very important. This is very, very, very important, okay? Not molecules. Am I clear, everybody? Is this clear, guys? Yes? Is this clear? All right. All right, everybody. All right, yes. Now we come to Hess's law of constant summation. This is also very simple, very easy. Just write it down, everybody, okay? If a reaction, Hess law says that if a reaction takes place in several steps, then what will it do is, it will consider that the standard reaction enthalpy is the sum of all the enthalpies, okay? Sum of all the standard enthalpies in the intermediate steps. Got it? Okay. What did he say? He said that, Hess said that if a reaction takes place in several steps, then its standard reaction enthalpy is sum of standard enthalpies of the intermediate reaction. Am I clear, everybody? Yes. Then there are different types of standard enthalpy as well. What are the different enthalpy of standard? What are the different standard enthalpy types? There is standard enthalpy of combustion. There is standard enthalpy of atomization. Yes, there is standard enthalpy. There is bond enthalpy. There is lattice enthalpy. All of these are there. Okay. So let's quickly write that down, everybody. Shall we? Let's quickly write that down. Shall we, everybody? Can we? Or no? Who is that? Yes, okay, chalo. Standard enthalpy types. Okay, what are the different standard enthalpy types? We have standard enthalpy of combustion. Let's write that down, everybody. Okay, standard enthalpy of Vivek, I do not know, Baba. When it comes, I will tell you. Shh, focus in the class, Baba. Baap re baap. Huh? What do you think? I'm NTA member or what? No, na. If NTA tells you what is the syllabus, I'll tell you. Chill, Mari. JEE syllabus has not been reduced. I have made endless amount of videos regarding this. I don't know why you keep asking me like this. Okay. What is standard enthalpy of combustion, everybody? Enthalpy change per mole of a substance. You know what? I'm not going to write down the definitions right now. Okay. Kinda standard enthalpy of combustion. Okay. Then there is standard enthalpy of atomization. What is atomization? Atomization means that you are breaking down a molecule into its atom, right? So that is your standard enthalpy of atomization. Okay. That is standard enthalpy of atomization. All right. Then there is something called as bond enthalpy. What is bond enthalpy? Bond enthalpy is basically the enthalpy of atomization, right? What is bond enthalpy, everybody? Bond enthalpy is basically the enthalpy of atomization, the amount of energy that is required to break a bond, right? Enthalpy of bond dissociation, correct? What is bond enthalpy, everybody? What is bond enthalpy? Bond enthalpy is enthalpy of atomization, right? It can either be enthalpy of atomization, which is equal to enthalpy of bond dissociation. Yes, everybody, right? Now, this bond enthalpy, it is only applicable for a diatomic molecule. What is it applicable for? This is only for diatomic. Now, what if the molecule is polyatomic? If the molecule is polyatomic, everybody, do you remember in chemical bonding chapter, we have read that when you are breaking down the bonds in a polyatomic molecule, it is not always the same equal amount of energy. At that time, we have to take mean bond enthalpy, okay? Yes, for a polyatomic molecule, what do you do? For a polyatomic molecule, yes, what do you do? You take the mean bond enthalpy. What do? You take the mean bond enthalpy. Am I clear, everybody? Yes, am I clear? Then comes something called as lattice enthalpy. Now, what is lattice enthalpy, everybody? Very simple. Simple. Lattice enthalpy, NaCl enthalpy change which occurs when 1 mole of an ionic compound dissociates, right? When 1 mole of an ionic compounds dissociate, that is called as lattice enthalpy. So, there is also something called as lattice enthalpy, okay? There is also something called as lattice enthalpy. Cool? Alright? Yes, great. Now we come to Born-Haber cycle. What is this Born-Haber cycle, guys? Born-Haber cycle is nothing but it is a way to calculate the lattice enthalpy. What is it? It is a way to calculate the lattice enthalpy. Alright? You know how in P block or in DNF block, we remember standard electrode potential we had calculated, and when we were calculating standard electrode potential, do you remember we had to calculate how a metal goes from its normal state to it goes to its isolated state. So you have to give it sublimation energy. Then from isolated state, you have to give it ionization energy twice to bring to take out two electrons, and then hydration enthalpy is released, and then it goes to its aqueous state. Something like that is actually your Born-Haber cycle. You want to see how it is done? Okay. So let's say that everybody, let's take the example of NaCl because I think that's the easiest and the most simplest form, right? So what I can do is I can take Na in solid form, plus what I can do is I can take half Cl2, right? Half Cl2 in its gaseous state, and what I can do is I can form NaCl in its solid form, right? Yes. Now this is my one-step process, correct? This is my one-step process, right? I can do this. And right here, I will get delta F, that is enthalpy of fusion, right? Enthalpy of fusion, right? Standard enthalpy of fusion will be here. Correct, everybody? Yes? Great. All right. Now, instead of this, what I can also do is from this Na, from this solid state, what I can do is I can take it to its gaseous state, right? I can take it to its gaseous state. Am I right? Yes. And at this point of time, I will have to give it sublimation energy. Yes. I will have to give it sublimation energy. Am I right? Now I do not want Na in its gaseous state, because how is NaCl forming? NaCl is forming because of Na plus in its gaseous state plus Cl minus in its gaseous state. Isn't it? Yes. Right, everybody? So from here, what am I doing? From here, from the gaseous state, I have to take it to Na plus. That means I will have to take away one of its electron. Yes. So here it will be delta IH, right? Enthalpy of atomization, because what am I doing? I'm taking away one electron, isn't it? I'm taking away one electron. And from here, when it goes to NaCl, that means here lattice enthalpy is involved, right? Lattice enthalpy is involved. Am I right, everybody? Great. Now let's do the same thing for your Cl. Okay. So half Cl in its gaseous state, when I have to take it, okay, when I have to take it to Cl gaseous state, right? Cl gaseous state. But here I have half. So what will I do? Bond dissociation. Cl2 is there. From Cl2, I have to take it to Cl. Yes, I need one single atom. So what do I have to do? Dissociation. Dissociation, because this is half, what will I do is I will divide it by 2. So H this, right? Yes. Now this Cl, when it goes to gaseous state, what will I have to do? I will have to give it electron gain enthalpy. Yes, Cl minus. So that means it has gained an electron, right? It has gained an electron, everybody. So that means that electron gain enthalpy here, everybody. Correct? Yes. And then it is going to this. Right, everyone? Yes. So everybody, if you check it out, then this process becomes a multi-step, isn't it? This becomes a multi-step process. So that means that here I can use Hess law, right? Here I can use Hess law, isn't it? Yes. So what does my Hess law says? Hess law suggests that delta F H naught. Why delta F H naught? Remember, see, this is the one-step process. So this one-step process is equal to all the intermediate steps, isn't it? This is equal to all the intermediate steps. So delta F H naught is equal to delta sublimation, yes, sublimation, plus delta atomization, yes, plus delta dissociation, right, plus delta dissociation divided by 2, plus delta electron gain, plus delta lattice enthalpy. Is this clear, everybody? Is this clear, everyone? Yes. Now we come to a topic called as dilution versus solution. What is solution? What is dilution, everybody? Solution is basically what you do is you take some solute and you put it in a solvent, right? Yes. What is solution, everybody? Solution is basically you take some solute plus you put it in solvent, right? Yes, that is your solution. What is dilution? In a solution, what you do is you keep adding more solvent, more solvent, more solvent, and that is your dilution, isn't it? Yes. So when I say that we also have to study about enthalpy of solution, then what do we have to study about, everybody? Yes, what is going to be my enthalpy of solution, everyone? What is my enthalpy of solution, everybody? Please have a look. What is enthalpy of solution? Enthalpy change when 1 mole of a substance dissolves in a specified amount of solvent. Yes, what is it? What is it? What is it? What did I say, everybody? Enthalpy change, everybody. Okay. Enthalpy change when 1 mole of a substance, okay, 1 mole of a substance, yes, dissolves in a specified amount of. So when you put it in a solution, what will happen? Yes, NaCl, when you put it in a solution, what will happen? It will become Na plus and Cl minus, right? It will become Na plus plus Cl minus. This is your one-step process. And then you can also put it in two-step process, right? But let's finish it. No, let's finish it, everybody. Let's finish it, okay? Yes, let's finish it. Chalo, for example, what am I trying to tell you is, see, NaCl, if I put it in a solution, right, what will happen? It will become Na plus plus Cl minus, correct? Yes. This will be my one-step process. This will be my one-step process, right? But what I can do is, I can also take it to Na plus in gaseous state, plus Cl minus in its gaseous state, right? And from here, this can release some hydration enthalpy. This can release some hydration enthalpy, right? And then it can get converted. And here, what will happen? Here, I will have to give it delta lattice. Yes, so this will become my two-step process. So once again, you can just use the Hess law and you will be able to find it, right? Now, what is enthalpy of dilution? Enthalpy of dilution is, bacha. Okay, enthalpy of dilution is, okay, let's try to understand this, okay? Let's try to understand this. Enthalpy of dilution. Please check it out, everybody, okay? Enthalpy of dilution. Let's say that HCl, okay? HCl in its gaseous state, plus let's say if I give it, let's say if I give it 45 units of aqueous, okay? 45 aqueous, then what will it become? It will become HCl dot 45 AQ, right? Yes. And let's just say that the delta H value here is, let's say that it is around minus 73.62 kilojoule. I do not know what is the actual value, okay? I do not know what is the actual value. I'm just saying it, okay? Top of my head, I'm taking the value. All right. Now, if I add, let's say, infinite units of water, then what will happen? This will be infinitely diluted. Yes. And at infinite dilution, what happens is delta H is equal to, let's say that it is around minus 74.90 kilojoule per mole. Let's just say, again, I do not know the data. This difference, okay, the difference between this and this value will be your enthalpy of dilution. What is it? Yes, what is enthalpy of dilution? The difference between this value and this value, okay. The difference between these two values will give you enthalpy of dilution. All right. Yes, that means basically heat withdrawn from the surroundings when additional solvent is added to the solution. What did I say? Heat withdrawn from the surroundings. Okay, from the surroundings when additional solvent is added to the solution. Clear? All right. And finally, somebody was asking, right, ma'am, what is spontaneity? Chalo, let's talk about spontaneity. What is spontaneity, everybody? Again, in your younger days, you have studied. Remember spontaneous combustion? Yes. For example, phosphorus, if you just expose it to air, what happens? Phosphorus catches fire. Yes, phosphorus catches fire. So who is going to decide that, okay, this is going to be spontaneous and this is not going to be spontaneous? We know that some processes, they just occur on their own and you do not have to give them any external, you do not have to give them anything externally for them to happen, right? So we understand that, but who is going to decide? What actually decides this spontaneity? Who decides all of this? Yes, who decides all of this? That we will talk about. But let's understand that a spontaneous process is an irreversible process and it may only be reversed by some external agency. What did I say? I said that a spontaneous process, my dear students, okay, a spontaneous process, yeah, a spontaneous process is an irreversible process, yes, and may only be reversed by some external factor, let's say, okay, by some external factors. Coolio? Yes, everybody. Do we understand this? Yes. Okay. And some processes, they occur on their own. They are called as spontaneous reaction. Okay. All right. So now, normally, you know what? Normally, we know that an exothermic reaction, okay. What formula, bro? What formula? All the important formula I'm telling you, no. Whatever formula you require, I'm telling you that. So chill. Yes. And if I miss out on it, then I will tell you what is it. Okay. For dilution, you don't require it right now. If you require it, I'll tell you. Tomorrow when we do problems, then we will complete a little more. Okay. Then we will do some more. But understand the basic concepts of it. Okay. Understand the basic concepts. We will do the formula and everything. Don't worry, Shreya. Don't worry at all. Okay. We'll do it. Chill. Tomorrow we will be doing problems. Okay. JEE means problems we will do related to thermodynamics so that we are crystal clear with the chapter. Okay. Chalo. So, normally we see that whenever a reaction is exothermic, most of the time what happens is that decides the spontaneity. But there are also examples where we see that there are endothermic reactions which are spontaneous. Very few, but there are. Okay. Very few, but there are. So, what can we say? Now we can say that the decrease in enthalpy, that is exothermic. When it is an exothermic reaction, what happens? There is a decrease in enthalpy, isn't it? So, decrease in enthalpy may be a factor. Yes, may be a factor, but it is not always the same. Okay, it is not always the same. So, coming to the point, somebody was asking, so what actually decides spontaneity? It is entropy. Yes. So coming to the question, what decides entropy? Okay, sorry. What decides spontaneity? It is entropy that decides spontaneity. Guys, I have to go to the washroom. Can we all please take a break for 2 minutes, everybody? Another half an hour, I think we are done. Yes, after entropy may we have to read about Gibbs free energy and spontaneity, second law and third law. That's it, that's it. Another half an hour maximum. After that, we are done. Yes, half an hour. So, but let me give me 2 minutes, please. I have to go to the washroom. Can I please go? Yeah, can I please go, everybody? Last 2-3 topics only we have, but I have to go to the washroom, guys. I want to see all of you here. But you just have to give me 2 minutes, everybody. Yeah, 2 minutes, guys. 2 minutes. In 2 minutes, I'll be back. But I have to take a washroom break. Sorry. Say hi. Say hello to everyone. Hello. Hello. Hi. See who is here. Say hi, Aman. Hi, Janvi. Very good. And this is my baby. This is my baby, Leo. This is my baby, Leo. Say hello to everyone. Say hello. Hi. 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 Okay, bye. Go out, okay? We will take the class and then we will say hi to you. All right, guys, we are back. I have 3 cats like that. I have 3 cats like that. All right, I needed a little bit of energy from my cat. I got it from him. Okay, guys, shall we continue then? Yes, are we back? Everybody refreshed? Everyone is fine? No. I dogs, they require a lot of space, yeah. And you have to like take them for walk, and then you have to give them a lot of attention and everything, right? So dogs are it's a little difficult for now. Maybe when I have a bigger house and when I have like, when I have a little less work, now I have so much work. See, if I had a dog, he would start barking and everything, right? That's why. Any real life example? Yes, real life example. For example, spontaneity. Have you this thing? Forest fire. You don't go and burn the forest, right? You don't go and burn the forest. But what happens is in hot summer days, yes, the dried branches and the dried leaves, they reach their ignition temperature and they start burning. So that is a spontaneous reaction. Okay, that is a spontaneous reaction. Yes, water will always flow downhill. If you want to put it back, if you want to make it flow the other way around, then what will happen? You will have to use a motor or something, isn't it? Yes, then you will have to use a motor or something. Got it, Janvi? So these are the examples. So chalo, a spontaneous process we have understood. Now what decides spontaneity? This is what we were talking about, isn't it? What decides spontaneity, everyone? Spontaneity is decided by everybody. Spontaneity is decided by entropy. Yes, and what is entropy? Entropy is a measure of the degree of randomness or disorder in system. Yes, or disorder in a system. So you tell me which state will have the maximum entropy? Which state has the maximum randomness? Everybody knows, I guess. It has to be gas, isn't it? Yes, it has to be gas. Everybody? Great. All right. So let's write it down, everyone, that entropy decides it, right? Yes. So let's talk about entropy then. Yes, let's talk about entropy. What is entropy, everybody? Yes, what is entropy? Please take questions. Bacha, questions tomorrow let's do, na? If I don't finish the chapter now and if I start taking questions, it will take even more time. Then the class will go till 12 o'clock. So let's finish all the concepts today. Questions I will take tomorrow. Pakka, promise tomorrow we will do JEE mains problems. Okay? All right. Yes. So entropy is a measure of, okay? Entropy is a measure of the degree of, okay? Is a measure of the degree of the randomness Bro, what do you want me to reply to that? I'm teaching, can't you see? Don't disturb now, no? Already 10 o'clock. Even I want to sleep. You want to sleep. Yes. So entropy, randomness or disorder in the system. Correct? Yes. Very good. Now we all know that solids will have minimum entropy. Correct? Who will have the minimum entropy? Always the solids, right? And what will gaseous be? Gaseous state will have the maximum entropy. Am I right? Yes, they will have the maximum entropy. Now, what else about entropy don't we know? Yes, we also do not know that entropy is denoted by S. Denoted by S, right? Entropy is a state function. Yes, it is a state function, everybody. Yes, and change in entropy, yes, Change in entropy is denoted by delta S, isn't it? Change in entropy is denoted by delta S. Okay, all right. Change in entropy is denoted by delta S. So now the question comes is that how do we measure entropy? How do we measure entropy? Okay, that is also very easy. Delta S, that is change in entropy, is actually directly proportional to Q, that is heat added to the system. Alright, yes. And it is inversely proportional to temperature of the system. Yes. So what did I say? What did I say, everybody? I've just said that delta S is directly proportional to, you know what, let me not write that down here. Let me just quickly write it down. Delta S is directly proportional to Q. Alright, yes, it is directly proportional to Q. What is Q? Q is heat added to the system. Alright, heat added to the system. Am I making sense, everybody? Yes. Alright. And delta S is inversely proportional to the temperature. Alright. So that means that what is my formula? That means that what is my formula, everybody? My formula becomes delta S is equal to Q divided by T. Makes sense, everyone? Yes. Does this make sense? Does this make sense? Now, what is the entropy for reversible and irreversible process? What is the entropy for reversible and irreversible process, everybody? Very easy, very simple, everyone. Understand and check it out. Have a look. For a reversible process, okay, for a reversible process, we see that delta S, okay, delta S of the universe is equal to 0. Okay, all right. And what is it for irreversible process, everyone? What is it for irreversible process? For irreversible process, we see that the change in entropy of universe is greater than 0. All right, yes. And if it is isothermal conditions, then what will happen? Delta U is equal to 0 for both reversible and irreversible, right? And for reversible processes, we know that delta S is equal to 0, and for irreversible process, delta S is greater than 0. Am I clear, everyone? Yes. Am I clear, guys? Is this clear? Is this clear? Yeah. Okay. Now we understand Gibbs energy and spontaneity. We're almost here, guys. We're almost here, everybody. Yes. Okay. So now we know that spontaneity depends on delta H and delta S. Correct? Yes. So what about my Gibbs? What about my Gibbs free energy? This Gibbs free energy was this Gibbs function, G. Okay. This Gibbs function G was introduced to understand that who is going to tell us that if the reaction is spontaneous or not. Okay. If the reaction is going to be spontaneous or not, who is going to tell you? That is why we have introduced another function, that is G. And you know what is G? G is equal to H minus Ts. Yes, G is equal to H minus Ts. Bole to delta G is equal to delta H minus T delta S. And what is this reaction, everybody? This is your Gibbs-Helmholtz equation, which is required pretty much in almost every thermodynamic question that you will probably see in your JEE Advanced or in your JEE. Yes, you will see that this is the reaction that is utilized. Okay, so what is this? This is your Gibbs-Helmholtz equation. Yes, this is your Gibbs-Helmholtz equation. All right. Now coming back to the point that how now see how we will understand that which one is spontaneous, which one is not spontaneous. Very easy. If by chance, okay, if by chance delta G is negative, delta G is less than 0, bole to negative. If delta G is less than 0 and if it is negative, then the process is spontaneous. Then you will have a spontaneous reaction. You will have a spontaneous reaction. All right. That means that delta H minus T delta S is less than 0. Yes. That means that delta H is less than T delta S. If this is the case, then you will have a spontaneous reaction. Are you understanding? Yes. Are you understanding? Cool. All right. Now we have if delta G is positive, everybody. Check it out. Delta G is greater than 0. That means if it is positive, then what we will have? We will have a non-spontaneous reaction. We will have a non-spontaneous reaction. Clear hai? Clear hai? Clear. Now we come to second law of thermodynamics. And what is second law of thermodynamics? Second law of thermodynamics says that in an exothermic reaction, heat is released by the reaction and that increases the disorder of the surroundings. Obvious, right? I am a system. If I am releasing some heat, then the heat is getting transferred to the surrounding. And in the surrounding also we have particles. The surrounding particles, what will happen? They will absorb the heat and the randomness in them will increase. Yes, so the disorder of the surrounding will increase. And overall entropy change is positive, obviously, because they are absorbing. Overall entropy change is positive, which makes the reaction spontaneous. And that makes the reaction spontaneous. Is that making sense, everybody? What is it? What did I say, everyone? Write it down, write it down, write it down quickly. In exothermic reaction, everybody, in exothermic reaction, in exothermic reactions, heat released by the, heat released by the reaction, increases the, disorder of the surroundings, and overall entropy change is positive, which makes the reaction spontaneous, all right. That means that delta S is greater than equal to 0. Yes, and what is the mathematical expression? The mathematical expression is right here, everybody. It is right here, okay? All right, this is the equation here. See, delta system plus delta surrounding if it is 0 for reversible process. Delta system plus delta surrounding is greater than 0 for irreversible process, and delta system plus delta S surrounding is greater than 0 in general, okay? In general, all right? Yes, everybody, got it? Clear? Chalo. Now we come to the third law of thermodynamics, and what is that? The entropy of any, this time we are going to talk about crystalline substance. Enough of gas. We have spoken about gas a little too much, isn't it? Yes. We have a, why is your teaching in a hurry? Ek maar khayega, you know? Huh? You understand a punch? I'll give you a virtual punch. I've been teaching since the last 3 hours. That time you were not there. Now that I'm ending the session, now you are telling me why is your teaching in a hurry? You guys, I swear, it is the hardest to make students happy. My goodness. My goodness. That is why teachers get angry and they start shouting. Now you understand why your school teachers shout? That is why. This is the reason why they do. I have started the streaming since last 3 hours. It is more than 3 hours. It's about to be 4 hours. Now why you're teaching in a hurry? Are you serious, bro? Anyway, what is the third law of thermodynamics? So we have spoken about gases a little too much. This time we're talking about a crystalline substance, okay? All right, so what is this? This time we are saying that the entropy of, any pure crystalline substance, it approaches 0 as the temperature approaches absolute 0. Do you remember what is absolute 0? When it is absolute 0, what was it? It is actually 0 Kelvin. 0 Kelvin is absolute 0, isn't it? Yes. So exactly. So the entropy of any pure crystalline substance, it approaches 0 as the temperature approaches absolute 0. Okay. All right. What is it? The entropy of any pure crystalline substance approaches 0 as the temperature approaches absolute 0. All right, and this is your third law of thermodynamics. All right, everybody. Yes, so here are a little more questions which I think we will do it tomorrow. Yes, and this is the mathematical form of third law of thermodynamics. As you can see, delta S here, right here, everybody, right here. This is your third law of thermodynamics. Okay, at 0 Kelvin by third law of thermodynamics, this is the most important part. Okay, this is the most important part. What is your entropy? Your entropy will be, okay, your entropy will be, everybody, yes, your entropy will be 0 to T Cp dt divided by T. Okay, you will have to do integration. Obviously, you will have to do integration. Is that okay? All right, everybody. So third law of thermodynamics is done. There are certain bit of phase transformation and all of these that you can just go through and you can check it out. Okay. These are all done. Relationship between H and U, enthalpy change of reaction, enthalpy of reaction processes. Anything else that I've left? Hess law is done. Entropy and Gibbs free energy reaction. This is also done. Entropy of reaction is done. Let's solve. I think with this note, we are all done, guys. That's it. Okay. Acha, here is a chart, everybody, that I please want you all to, that I really want you all to, that I really want you all to go through. Okay. This chart is very, very, very important. Okay. This chart is very, very, very important. Please go through it. Everything is written here. All the different types of processes, their graphs, everything is right here. Okay. Everything is right here, written here. So please go through it. Okay. Please go through it. And I think with this note, we are done with the session. Tomorrow, I think at around 7 p.m., 7:30 or 8 p.m., we will be doing JEE Mains thermodynamic questions. And I believe that I have also asked my channel manager to schedule general organic chemistry nomenclature of cyclic compounds. So we will probably be doing that around 4:30. All right. So I'll see you tomorrow, everybody. With this note, it is. Even Pratik sir is taking thermodynamics. So great, no? You will be done with both physics as well as chemistry, thermodynamics at the same time, isn't it? You'll be done with both of this at the same time. Yes? You were regular in this session. Thank you so much, Komal. Thank you so much, Kamal. Acha, sending you the PDF. Chalo, sending it to you right now, everybody. I will be sending it to you right now. You can see it. Yeah. I'll be sending it to you right away. Yep. Here. Send it. Quickly go and join the Telegram channel. If you haven't joined the Telegram channel is right here in the description box, everybody. Yes, if you want, I will also show you. Yeah, if you want, I will also show you. Don't worry about it. Let me show you quickly. Yes, here. So I have sent it, everybody. Okay, I have sent it, everyone. And wait a second. Let me show you the Telegram channel. So this is where I'm taking a live session, isn't it? This is where I'm taking a live session, as you all can see. Correct? And if you just click on this more, do you see this more, everybody? Just click on this more. Once you click on this more, see right here, you will also get the crash course link, everybody. Okay? You will also get the crash course link, everyone. Okay? All right. So just click on this. Kirchhoff's equation I have not done yet, Kamal. We will see tomorrow while we are solving the problem. At that time, I will see if we can do it. Okay? At that time, we will do it. Yes. Ravi Kumar, STP is standard temperature and pressure and NTP is normal temperature and pressure. Yep. Okay. All right, everybody. So you just have to go and join our Telegram channel. This is our Telegram channel. And if you guys are still struggling, okay, if you guys are still struggling to understand your sessions and to understand what is going on and everything, then what you can do is you can just quickly go and enroll. Okay. You can just quickly go and enroll in a live JEE crash course, and that is there in the description box. Okay, that is there in the description box. So with this note, everybody, tata, bye-bye. Thank you so much. Lots of love to you all, those who have been in the session here. Okay. Lots of love and all the very best. Good night. Have a nice day ahead. I'll